Hello, good morning. Welcome back to Thursday. And it's my pleasure to present the first speaker of today, Yehuda Shalom, and I'm going to talk about conjugation invariant norms on groups. Thank you very much.
Thank you very much. Okay, thank you very much for organizing and having us here in this beautiful city and this very good conference. So I would like to talk about the joint work with Leonid Polterovich and Zika Shemto here. Maybe yes. Okay, so we join with Leonid Polterovich and Shemto. And what I would like to talk about is the notion of norm or group, which leads to, as I hope that you will see, it leads to very interesting kind of setup that can combine classical and very deep rigidity results and leads to questions, further questions, strengthening of some well-known rigidity results, and it's a kind of interesting setup. So I would say, in the title of the conference, I am more towards the last word of the title. So we've seen a lot of sub-riemannian geometry, and I will concentrate on the beyond. It's a metric that we're going to look at for groups, but it's a slightly different kind of metric than the one that we're used to seeing here in the conference. So let me just understand that this is not in the frame. So I just wrote the definition. It's a very easy definition, seems very elementary. So we start with an absolute group G, and just for brevity, I'm going to call it a norm, even though one should better emphasize that we're looking at what's called the invariant or conjugation invariant, if one wants to be really precise. So a conjugation invariant norm, which again we're going to just refer to as norm, on a group G. Okay, so it's a way of assigning a non-negative real number to any element of the group, which satisfies very natural conditions. So the norm of an element is zero if and only if it's the identity. So here we see something which is very close to distance, of course. We have the triangular inequality. We have this, of course, the norm of an element and its inverse should be the same. So all these are not a surprise to us. And the fact that it's actually conjugation invariant comes into play in this last property that the norm of a conjugate is the same as the norm of the element. Okay, and the way this relates to the usual notion of metric is by this very, very trivial observation that any such norm induces a B-invariant metric. So it's a metric. Usually in conference geometric theory, we look at metrics which are invariant under the action of the group on one side. Here we have, a left and right action, and from such a norm, you can cook very easily in this definition a B-invariant metric from both sides and vice versa. Okay. So these are, I'll just leave it here. Basic definition. So this is the notion that we're going to look at first. Okay. So the most kind of, I think the most of the activity, the attention, this notion started with the actually in the context of selective geometry, when Hofer constructed this well-known construction. So there is, I think it's started. So there is this B-invariant metric on the group of Hamiltonian D-fields, a symplectic manifold, and this is a very important construction, and this is of course this is an infinite dimensional, so to speak, an infinite dimensional manifold where it gives you an infinite dimensional group which has this this norm, this invariant metric, or this norm that is defined here. And in fact, some of the results that I will mention here do have implications once you plug in Hofer's metric into those results. I will not concentrate on this geometric aspect. So here I should put the name of Polterovi, Burago, Ivanov, Polterovich. And if you plug the results that I will, some of the results that I mentioned here, into this construction, that these symplectic manifolds meet this kind of metric, you get some interesting results. The problem is that this metric is still extremely mysterious. It's very difficult to understand which groups are discrete or not in this Hofer metric, so it's still largely not understood, even though it's an extremely deep and considered a very basic construction. So it seems like the interest in this kind of norm started here in this geometric setting, but later on people started to look more and more on these norms, and I will not, so many names are associated. I will not drop, most of them I will just maybe skip, but it started moving on. Okay, maybe other norms that appeared were in the context of discrete groups, commutator length, word length, and slowly it started to appear in different contexts. I will mention, hopefully I will have time, I will mention that these norms also appear in the context of, which is now very fashionable, the context of approximation of groups, like Sophie groups, hyperlinear groups. These are major open problems, and these are also related to, so for such approximations, one can construct in a very natural way a B-invariant metric on a group. And again, our results, hopefully I have some time to mention this. Some of the results will have implications in that direction, maybe pointing to the existence of a group. Like this is the holy grail, the existence of a group which is non-sophic or non-hyperlinear. But again, this is like, again, at the background. So let me start be more concrete about what we want to do. So it seems that until the work that I'm about to present, this is just being accepted for publication, so it's fairly, I mean, it's been around various versions, but only like recently kind of we came to the final kind of shape of things here, which I want to present here. So most of the work, or actually before this work, all the work was concentrated on questions of boundedness of the norm. Okay, so let me come back to this introduction here. So I'll just mention an obvious remark that if you take any group, so here I deliberately say abstract because later on in a minute we'll talk about discrete groups and about compact groups. Okay, so I want to keep it very flexible. But whatever group that you take as an abstract group and you take such a norm, then you can always complete the group with respect to this norm. It's very easy to see that you get a topological group. And what we are actually interested in, and this is kind of the first kind of new angle that we kind of introduced into this issue, is that we are not interested in boundedness, like whether some norms are bounded or uniformly bounded on some groups, but actually we're interested in the topology that certain norms induce on the group, which means what is the completion, okay, of the group, understanding the completion of the group with respect to this norm. So we are interested in the topology such norms induce on groups. Okay, so if you take, so this is, so let me just denote it in a kind of obvious way. This is always a completion of G with respect to G. This is always a topological group, which typically is very, very large, okay? But it can also be a discrete group. So this leads to a very natural notion of a discrete norm. So here is the definition. And this gives us the first examples, which are kind of easy of such norms. Very natural examples that will, serve us throughout the talk. So a norm is called discrete if it generates the discrete topology on G. Let us spell it out. What does it mean? So there is some positive epsilon such that for all G non-identity, the norm of G is at least epsilon. And it is called, okay, so this is the first, so discrete norms are obvious, right? I mean, and every group admits such a norm, say 1 on every non-identity element and 0 on the element. So this is the first source of trivial norms that every group has. Another source of norms that every group has, sorry, not every group, but some group have, would come from embedding into a compact group. Okay? So recall that every compact metrizable group K, so this is kind of classical fact, admits a bi-invariant metric B, which, as we said here, right, any such metric really corresponds to a norm. So there is a norm on K, and therefore, whenever you have, so this implies that if you have an embedding, if you have an embedding of your group inside such a compact group K, where K is as compact as above, so this induces, so let's say every induces a norm on G through its embedding inside K, induces a norm on G, which we call a compact norm. Okay, intrinsically, this is equivalent to saying that the completion, as we just wrote here, the completion of the group with respect to this norm would be a compact norm. Okay, so this is the notion of a compact norm. Okay, so what are examples? What would be a very natural example of such a norm? Natural, this is important for us. A natural example, of course, some examples come from simply discrete, dense subgroups of compact groups. So whenever you have such an embedding, as we said. But another example, which is important to us, is that whenever if G is a residually finite group, okay, so remind you, residually finite means that the homomorphisms into finite groups separate the elements of the group. Then you can always construct this for finite completion. Then one can take K to be its for finite completion. And thereby, so this would give you, for any residually finite group, this would automatically gives you, so a compact norm on G. Okay, so these are two very easy sources of norms, and the purpose of the talk is to discuss various situations where these are the only ones, and what kind of rigidity result this relates to. And also to highlight the very interesting duality kind of feature between the discrete and the compact. But let me just mention still at the last point of the introduction, the last stage of the introduction, there are some very exotic norms which are known that the earlier that we could find is from 1970, just to indicate that this world is quite wild. So there is an example that we could, probably this is, I don't know, seems like it's the first one. Yes, you spelled it. So an exotic norm on Z. Exotic, I mean, the completion would be a non-locally compact group. Okay, so, and this, it's not difficult to see that this can actually be upgraded. And this is quite a tricky construction. I mean, you have to work for it to, you know, it's something which seems so elementary. You just want to, and of course, when the group is abelian, then this condition is trivial. So you just have to construct this, you know, just deal with these three properties. But it turns out this is not, you know, one has to work a little bit to construct interesting, like non-locally compact norms even on Z. But once you have this, then it can be upgraded to every group with infinite center. So just to indicate that immediately bad things can be lifted and can be used to create more and more bad things. Okay, so to contrast this with some rigidity results we are about to talk about. Actually, infinite center. Yeah. Z is actually the, when you have an element of infinite order, you use Z, otherwise you use other tricks. You're right, the question is correct, it's natural, but you can actually, this is the most, the trickier part when dealing with an infinite center, but anyway, you can do it. So many groups would have exotic norms, okay? So as I said, we are going to be interested in duality, kind of also feature between the compact and the discrete norms. And so let me put the central definition that we're going to use. Okay, so definition. A group G has the dichotomy property if every norm on G is either discrete or compact. Okay, so in mind we have G, so we have G, which is itself either discrete. Let's say, okay, we want to assume, we assume G is residually finite. For this to be just as a technical, I mean, in the definition, it's not a result, so I can assume whatever I want, but so this makes, so for us, the interesting things to think about is either G is discrete, or it is itself compact, which means because it's residually finite, or it is a compact or finite group. Okay, so these are really the examples to think about. Okay, so this is the kind of rigidity phenomena that we are interested in. You know what? Let me not put it. I see that I eventually decided it's not a good idea to put it in the definition. Yeah, probably this also would answer. Let me not put it here, but rather put it in the. Yeah, let's just make it clean definition, and then it will appear in the next result. Okay, so this. I also said it. Yeah. Okay, so here is now a proposition, which hopefully already shows you that this would be. Right, so assuming, no, so I'm saying, here, yes. Yeah, we don't just, sorry. Yeah, exactly. So when I say compact norm, it means the completion with respect to the norm is compact. Discrete norm is obvious. So when I talk about properties of a group, I'm only interested in topological properties of the norms. And when I refer to the topological properties of the norm, I mean the topological property of the completion of the group with respect to them. Okay? Okay. Okay, so let me put here the proposition normality, which for the first time puts us into business, really, a normality proposition, which shows the following. So suppose, so I'll put it here. So suppose G is okay, so here I would like to assume that it's either discrete or compact profinite. You'll see that this is profinite group which is residually finite and residually finite. Okay, so G is a residually finite group, okay? And I am looking at a group which is either discrete or compact. Okay, that's what's going on. So I should say maybe suppose that G is residually finite and it is either discrete or compact. Because residually finite means really that it's a finite group. Okay. Then the first result I want to mention here is that every normal subgroup of G has finite index. Okay, so this is the first thing. And the second would be that every so every normal subgroup of G is open. Of course, this would be trivial in the case of when G is discrete, but it is highly interesting, and I will hopefully have time. Yeah, probably will have more time to say about this relation to a very deep conjecture of Sauer. Yes. Oh, yeah. Suppose G has, of course, thank you. So suppose G satisfies the dichotomy. Okay, thank you. Okay. And it is either discrete, okay? So this is a residually finite group, which is either discrete or profinite group. And then we see that this kind of property gives us a very strong conclusion on the structure of normal subgroups. In the case of discrete group, the most interesting part is the fact that every normal subgroup has finite index. In the case of a compact group, which again, it must be profinite group, like totally profinite group for a compact group just means it's totally disconnected. This is the like a group like SL2 of the p-adic integers, you know, the kind of groups we hardly see in this conference, but they are very interesting. For compact groups, this is the more interesting feature, and it's, I will say a few words about it. This is related to a very deep, so it was a conjecture of Sauer that was a big work of Nicola Segal some 15 years ago, spanning dozens of pages, like papers in Annals and Editionen, and proving that conjecture. So these are the two things that I want to mention here as a corollary, as an application of the dichotomy property. And let me just maybe, yeah. With a finite group, it's actually a solved question. It is not stable even under passing to a finite index subgroup. It can be ruined very easily. I don't want to get into. Every of course, thank you. Non-trivial. Thank you. Yeah, every non-trivial normal subgroup G is finite. Oh. Okay, so let me just prove to you one, so that you get to play with it a little bit. Okay, and I will indicate the idea in the proof of 2, proof of 1. Okay, so let N be a normal subgroup of G, and let's denote by this the restriction of either the norm, either the profinite norm that G has as a compact group, or if G is discrete, then simply the profinite or the profinite norm constructed on G as a discrete profinite group, as a really finite group. In a minute, we'll give examples. Everything will be okay. Let's see this. We can. Okay. Okay, so we have this norm. We can assume, we may assume it's bounded. We may normalize, so we may assume, for example, that this norm is bounded by 1. Okay, for every n in our normal subgroup. And now define a new norm on G. Define it like this. So the norm of an element would be defined as, so it would be either, let's say here we have 1, so it would be 2 if G does not belong to N, and it would be this norm that we just defined if G does belong to N. Okay, so it's easy to check that this is a norm. And then there are two possibilities, right? You construct the norm of the group. The group has the dichotomy property. So this new group is either discrete or compact, and you just check that the different possibilities, the two different possibilities. So either, so if this is compact, what does it tell you about N? If this new norm is compact, then N has finite index. And if this norm is discrete, then N is finite. This is very easy to see. Okay, so this already tells you that groups, residually finite groups. So for example, okay, I should perhaps mention every finitely generated linear group is residually finite. Most of the groups we are interested in, discrete groups, are residually finite. So this is not really a serious, well, it's a serious assumption in the jungle of discrete groups, but it's a very mild assumption in our nice world of linear groups. Okay, so this is really okay. And then what we see immediately here, that whenever you have a residually finite group, so for example, as I said, a finitely generated linear group, then having the dichotomy property gives you a very strong restriction on the structure of normal subgroups. So for example, a free group cannot have the dichotomy property, and many other groups that these are kind of rare groups that have this property that every normal subgroup is either finite or finite index. And of course, this is very much related to the deep theorem of Margulis, the so-called normal subgroup theorem of Margulis. So I will in a minute talk about this. Okay, so let me say, maybe I don't have time, but I will let you play maybe with the second. For the second, I would just say maybe one word. So every non. Oh, sorry. Wow. Oh, I'm sorry. Every non is either, sorry, as or, wow, I'm so sorry, as finite index or it is finite. Yeah. I'm sorry. I am sorry. My bad. Okay. So every non-trivial, namely, it's not the identity, normal sub of G is either has finite index or it's finite. You cannot escape this. Okay, being finite index. Okay, are we on the same page? So these are the two possibilities for normal subgroups: finite index or being finite, and these two correspond to the once you write the norm, they correspond to the different situations of a compact or a discrete. Okay, thank you very much for this remark. Okay, so the second, so this is proof of one. For the proof of two, I don't have time, but let me just say proof of two. So the ID uses the observation that if all non-discrete norms are compact, then they are actually equivalent. Then they are actually equivalent to each other. Hey, I will let you think about it if you're interested. Okay, so in a minute I will say more about this. Let us now give some concrete results about the dichotomy property. It was a kind of a build-up, or maybe I would just say, okay, we'll just say this, that one. So I will put it on the blackboard here. One is strongly related to Margulis' normal subgroup theorem. The famous result says that any higher rank lattice satisfies exactly this property, that every non-trivial normal subgroup is either finite or has finite index. Well, I guess once I put it like this, then the word non-trivial does not need to appear here. It was one last polishing of the. Okay, so it's just every normal subgroup of G has finite of G is finite. So, wow. Yeah. No. This proposition, it says that if you have a group with a dichotomy property, then. So I'm not sure I understand.
Yeah, in the first conclusion, you say that it's either finite or finite.
Yes.
Then the second part, you say both
so yeah, I wanted to separate them because they kind of relate to the two different. The first one is mostly interesting in the context of discrete groups, and this is what I say here in the context of Margulis' normal subgroup theorem. In a minute, I will say something about this. Okay. So for a discrete group, this is a very, let's say, a linear group. As I said, they're always residually finite. So these are deep results. Whenever you have a discrete group for which you can prove this result, it's a very interesting, fact about it. And the second one is actually very interesting in the context of compact profinite groups. So 2 is related to Serre's conjecture. And as I said, Nikolov Siegel. Yes.
The question is ... But do you mean every finite index subgroup is open, or do you mean the same as above?
Every normal you know already that every normal subgroup has. It's true that the way Serre formulated is for a finite index subgroup,
but if it's finite,
exactly,
it's
so,
not open.
I see.
Then it's
okay.
not.
So yeah, thank you. So every finite. Okay, let me just be concrete. Every finite index subgroup. If this was the question, sorry. Of course, not every finite subgroup is. So every finite index subgroup is open. Does this answer the question? Okay, I'm sorry. Yeah. this is the price of changing the way you want to formulate theorems in the last moment. Yeah. Okay. Now we converge to the final. Okay. So these are the two. Okay. So the second, as I said, the first one is related to this deep theorem from what is the second to Searle's conjecture and this work about finitely generated profinite group. Okay, we'll see how time goes for us. Oh, okay. Yes. Sure.
If you project your finite index, the group on the quotient by your finite index subgroup, that's continuous map. That's a continuous map on a finite group, and the preimage.
But the problem is that it's the norm is okay. Yeah.
The norm is not continuous.
No, the norm is going to be 0 on this normal subgroup. This is what you want.
The subgroup has to be closed or not?
No, that's the whole point. That's the whole point. This is the issue here. Okay, so maybe I will say, because I can see for this, certainly for this audience, it can be confusing. So Sarah asked for finite groups. One can, these are compact. Wow, there is an echo. These are compact groups which are kind of built out of the finite quotients that they have. Okay, and Sarah asked, is it true that the topology is determined by the algebra or by the group theory? Okay, is it true that every finite index subgroup of a profinite group, which is finitely generated, so finitely generated profinite group means that it has a finitely generated dense subgroup. Again, very general natural condition. So Sarah asked if every such group has the property that actually all its finite index subgroup are automatically open. Now, every finite index subgroup contains a finite index normal subgroup. So it's really about normal subgroups, and this property is something that you get here. Okay, so they proved it, Nikolov and Siegel, they proved it in full. And as now we're going to state some positive results. And this result would give us a strengthening of this work of Nikolov and Siegel to. And we actually, well, I kind of believe that actually this strengthening might hold the key to a more general results. But these are so, the work of Nikolov Siegel is so involved. As I say, it uses also the classification of finite simple groups and like two very, like it's a really huge body of work. So it's not something that it's easy to kind of try to modify and so on. Okay, so let me finally state some results about it. So far we have, we are kind of around the issue. And in terms of the mathematics, so let me, where should I perhaps, so dichotomy I want to have here. Let me just put it here maybe. So I'll put the theorems. Okay, so theorem, let A be an integral domain change the integral domain with 1. Okay, maybe I will just check that I don't. Yeah, and assume that every non-zero ideal of A has finite index. Okay. So, for example, when we want to think about Z or rings of integers in number fields, or even FPT, if you come from the positive characteristic world, a ring of polynomials over a finite field, these are good rings for us. Also, something like Z1 over P is a good ring for us. Okay. Okay, so the result says the following: if SLN of A of this, so you look at SLN over this ring, has bounded. Okay, let's assume. So, okay, right. Assume n it is at least 3, and if SLN A has bounded elementary generation, I will remind you what this means, those who do not know. It's a very interesting property. Bounded, okay, so this is bounded elementary generation. Then this group G SLNA has and it's, well, this is a kind of and it's finite index on normal, it's finite index subgroups. This actually requires some work. It's not automatic, it's finite index subgroups. We did not want to keep, to be left out only with this group, but we actually had to extend this to finite index subgroups. This requires a lot of effort because in general, the dichotomy property that I'm about to mention here does not pass to finite index subgroups. So then SLNA has the dichotomy property. Okay, so even if you just look at the Z, so for example, you look at SL3Z, okay, just even fix this group. So SL3Z has the property, the dichotomy, which means that every norm that you take on SL3Z is either equivalent to the discrete norm, which is obvious, or it gives you the compact. And in fact, the result says more, it says more precise. It says that the completion is not just compact, but it's actually profinite. So the completion with respect to this norm would be a profinite group. Okay, compact profinite group. And then because of the congruent subgroup property, we actually know exactly what it's going to be. All the norms of this group are going to be of arithmetic type. They come from, so they would essentially come from something like SL3ZP product over P prime, some set of primes. Okay, we kind of, these are the compact norms that you get here. And in this sense, it's very interesting to view this result as a non-abelian analog of Ostrovsky's classical theorem. Remember that Ostrovsky's theorem tells you that every non-trivial, every valuation on the field of rational numbers is either R or QP. And similarly, you can state his result for Z. So you look at the integers and again, talk about valuation on the integers. So he tells you that all these valuations are either understood completely. And this is a kind of a non-abelian analog. So instead of evaluation, you talk about a conjugation invariant norm, and all the norms either, well, maybe I should have stated the Ostrovsky's theorem in the following way. So if you look at Z, then every absolute value which doesn't make, for which Z is not discrete anymore, comes from the p-adic, is arithmetic. It comes from the p-adic world. And this is exactly what you see here. Every norm on SL3Z which makes it non-discrete comes from the p-adic world in a very, but this again requires also knowing the congruent subgroup property, another deep result that you have to plug in order to understand precisely what are the completions. Once you know that the completion is profinite, then you use the congruent subgroup property and you can completely classify this. Okay. So as we've seen here before, because of the normality proposition, this gives you a different proof, algebraic proof, and such proofs, of course, were known for the normal subgroup theorem of Margulis. That right, because of this, it in particular implies that SL3Z or groups of this type satisfy this, part one, that every normal subgroup name is finite or finite index. But then it brings out the very natural question: what happens with the anisotropic case of arithmetic groups? So groups of this type, which are lattices in higher rank algebraic groups, but they are co-compact. So let's say a co-compact lattice in SL3R. Okay, so Margulis' theorem is known for such groups. it's a beautiful fact the way that this is proved. You know, it's an algebraic result, but it's proved by very analytic tools. Margulis called this result in his autobiography the best proof that he had in his career, the normal subgroup theorem. But so this would suggest a way, perhaps, to kind of generalize the normal subgroup of Margulis to these groups. So, and it brings the very natural question: is it true that, and we really believe that this is the case, that all higher rank lattices actually satisfy the dichotomy property? But this seems very, very far. I mean, it's very tough. Okay. Okay, so this is one direction of things that we take. Maybe I should I should remind you what bounded elementary generation means, and the fact that it's actually satisfied for all these groups is a non. It's kind of elementary in its statement, but all the proofs that I announced for this use the Dirichlet's theorem on primes in arithmetic progression. So what is bounded elementary generation for SLN? It means that there is some. So if you fix, say, SL3Z, then there is a number, 50 works here. So every matrix in SL3Z is a product of at most 50 elementary matrices. Okay, elementary means ones in a diagonal and 0 everywhere besides one entry. Okay, so every matrix in SL3Z is a product of at most 50, and the number, there are bounds for in all of these cases which are known, and it comes from number theory. Okay, so this is, if somebody could find, this is elementary result that you can state it to first-year students. If somebody can come up with a proof that doesn't use Dirichlet's theorem, this would be very, very interesting. Anyway, so this property is known for a large class of groups. An interesting feature that arises here is in the case of SL2. SL2Z does not have you are not surprised, of course, it's a virtually free group. It does not satisfy the dichotomy property, but you can ask, what about SL2Z 1 over P? So this was to us a bit, so out of, I mean, we could not immediately adapt our methods, but Trost after, so this was Trost realized how to actually modify our methods to cover this ring in the case of SL2 also, which is kind of compatible with basically what you need to work with is only a ring with infinitely many units. Okay, so this is one aspect of things that, this is one direction of things that one of the main results here that, you know, there are a large class of discrete groups which satisfy the dichotomy property, and this is a very strong generalization of Margulis' normal subgroup theorem. Maybe I will change a little bit the order of things. I will also say that this kind of construction also leads to a very interesting construction, which is related, before I move to the compact setting. It leads to a construction. So there are very interesting number theoretic constructions. So another application, there exist finitely generated, even finitely presented subgroups. Let's say interesting. I will explain what I mean. Interesting, finitely presented groups. Okay, I will explain with the property groups gamma such that for them every norm is discrete. Okay. Now, such constructions were known, but they were always groups which are boundedly simple. So, for example, if you want to show, it's easy to show that SLN of the rational numbers is such a group, because it's kind of a strong form of simplicity. They are boundedly simple. There is, from any element to get to any other element, you can get by finitely many boundedly many conjugates and multiplication. So this makes these groups easy candidates for groups for which every norm is discrete. But what is far more interesting is constructing such groups which do have lots of normal subgroups. Okay, so this is a construction. So gamma is a finite central extension of a group like, for example, SL3 Z1 over P. So this is a finite central extension. Of course, such a group for which every norm is discrete, it cannot be residually finite, because such group would always have compact norms. So it's very interesting construction in itself for classical by now that such finite central extensions exist, which are not residually finite. And one can push this further to show that these groups, these finite central extensions, actually have the property that every norm on them is discrete. So they are not residually finite, but they have lots of normal subgroups, which means that one cannot argue in a kind of argument which is similar to the boundedly simple construction. You cannot get from any element, you cannot do a trivial argument there. And these groups are, I see that I really don't have time to discuss the relation between this property and approximation properties of groups like sophicity or hyperlinearity, but the fact that every norm on a group is discrete gives some uniformity obstructions on the approximations that a group has. And such finite central extensions are among the natural candidates. Many believe that they would be good candidates for groups which are not sophic or not even hyperlinear. So anyway, I just want to mention that these are interesting examples of a different kind. They are not kind of trivial examples like these, which are really obviously have this property of groups for which every norm is discrete. So kind of very locked. Okay, let me use the remaining of the time that I have to discuss the compact setting. Okay, so maybe, yeah, I guess. So result that we have about the compact groups. Didn't miss anything. Okay, so theorem. Let A be a compact metrizable ring with one, and again with the assumption and assume every non-zero ideal of A has finite index. Okay, where does it come from actually? Here and in the previous result, right? Also here, I assume that every non-trivial ideal has finite. Why is it a necessary assumption actually? Because once you have such an ideal, you have a natural homomorphism from SLN A to SLN A over I, and it gives you a non-trivial normal subgroup of infinite, which is not finite and not of finite index. Okay, in order to get the dichotomy, you have to have this property that every such ideal has finite index, and this also appears here. So let A be a compact metrizable ring with one. We want to assume that every non-zero ideal of A has finite index. And then SLN. So let me just then SLN. And again, n at least 3 SLN A as a compact group. So think of A, for example, the p-adic integer, the ring of p-adic integers, or rings of this type. So then SLN A as a compact group now, because A is a compact ring, SLN A has the dichotomy property. So again, in light of what we have here, this immediately also proves that every finite index subgroup of this guy. Okay, so maybe I'll put here example for this result. SL3 of ZP, the ring of P, okay, has the dichotomy. And this is a strengthening of the fact, but this was already known to Sauer. Sauer proved that every pro-P, pro-finite group, satisfies this, and then he conjectured or asked the more general question about every pro-finite group. So this proves for these groups, for example, that every finite index subgroup is open. Okay, so this is one class of groups that we have for them the dichotomy property. And maybe I'll So second part of the theorem if G is a compact Lie group, real or p-adic. Okay, so p-adic analytic group, so this is a large family of groups, then again, G has the dichotomy property. So another general class of groups. Now here, not all of them are profinite. We actually say here that SON, when n is at least 3, SO2 does not have it. It's an abelian group, because we're not surprised it doesn't have rigidity results. But SUN, SON, and so on, compact Lie, simple compact Lie groups do have the dichotomy property. So it's not that much interesting in terms of the normality proposition. It doesn't tell us anything really interesting in this context, but it does give us very interesting automatic continuity results. Okay, well, what is interesting? I find it actually, kind of, again, it's a strong generalization of simplicity of this compact Lie groups. And it does give you another kind of application of this kind of dichotomy property and a discussion about norms, results about automatic continuity. So you get that every homomorph, once you have this, yeah.
You want to say simple compact? Simple.
Oh, sorry. Thank you. It's good to have you here. So yeah, simple compact. So for example, e.g., as I said, SON, when n is at least 3. Okay. Because otherwise it's a finite index. Don't think it will in this case hurt me. If it helps, I would put connected, but I don't think in this case I would, yeah. Anyway, it does give you, and this is a different aspect of this rigidity property of being having the dichotomy property, that a large class of homomorphisms of this group, for example, into other compact groups, they will be automatically continuous, because on the image you would induce the norm that you have on the image. This would give you a norm on your group. Now, if you know that the norm that you got on the group, as I said, once you know, it's a easy trick, that once you know that all the norms are compact, then all of them must be actually equivalent. So for a compact group, this actually means that the only norm that non-discrete norm that you have on the group is equivalent to the original norm that it has. So once you have this, you get that large class of homomorphisms. Well, homomorphisms of these groups into target groups, which have on them be invariant norm. For example, the Hofer metric in the context of symplectic geometry, the target has this by invariant norm. You can induce that norm on the target, induce it through the homomorphism on your group G. That now you know that this norm is equivalent to the original norm that induced the topology on your compact group. So it gives you an automatic continuity result. Okay? And they are very wild. Let me just end by showing you a wild construction to give you something that you have to encounter. Suppose that you look at ZP, because I feel I didn't have enough examples here and maybe not enough time. So here is a construction of a wild construction on a construction of a wild norm on ZP. ZP is inside QP, right? So QP as a field, of course, can be embedded in C abstractly. So this gives you an embedding of ZP as an abstract. And remember, I don't require anything about my norm. It can be anything. This is what makes things so tough. No continuity, nothing. So ZP can be embedded inside C, and C has its own, of course, the usual distance on C. So this induces a norm on ZP. And you can twist it even more, and you can use actually this kind of construction. You can twist things here by abstract automorphisms of the field C. So this would give you lots of norms on ZP, which are, of course, far from being continuous. So you can use this kind of construction, again, to show. So this is very flexible, but once you put things inside SL3ZP, they become very rigid. This is kind of the context of the result that I mentioned here, that groups like SL3ZP, this has the dichotomy property. You cannot play with this group in the context of putting it into a target and playing with stuff. It will be very rigid. Right. You can put it as SF3C, but it doesn't contradict anything. I mean, you can, but I'm not saying that every abstract homomorphism of SF3 ZP into SF3C is the standard one. I mean, it doesn't contradict. I'm saying here I did construct different. Here, when the target group has such a norm, of course, there is a limitation. It doesn't say that any homomorphism in the world, whatever, is continuous. But it does say that when the target has most actual, this norm, for example, for this group, if you look at using the Hofer metric, so if you look at this action on a Hamiltonian, on a symplectic manifold, it gives you a rigidity. And again, as I said, it's because the Hofer metric is not well understood, it's not entirely clear how to, in many situations, how to actually, what does it lead to? But anyway, so it does what it does. It tells you that in many situations you do have rigidity for this compact group in terms of homomorphisms into target groups, and this is a different feature that you get out of this dichotomy property. Am I guess started late, so I guess it's okay. Okay.
Thank you very much for the nice talk. Other questions?
Yeah.
There are many.
It's not a question.
So, what you're saying is you cannot put abstractly SL3ZP into a compact Lie group.
Exactly.
That's
one of the things.
One of the things.
And in fact, any p-adic analytic, any simple.
Yeah.
Simple here, I mean, in terms of the Lie algebra, yes.
I also start with a comment, and then this will lead to a question. So there is a result of Milnor. They say that if you are on a Lie group, and then you take a B invariant Riemannian metric, then this gives this. So a Lie group admits a B invariant Riemannian metric if and only if it is compact times vector space. Yeah. How does this relate with
so
this
if you want to put it into our context, it means that every homomorphism of the groups that we have here, okay, so if the target is one of these groups that Milnor in Milnor's theorem, then the target would be either discrete, okay, or compact closure. Okay, which setting? If you start with a discrete group, it means that okay, in this case, yeah,
we have a connected Lie group.
Right.
And for example, like the result, you have to add simple. But what about if the group is not simple?
So if it's semi-simple, then again, you get a version. You cannot really, I cannot say semi-simple by simple reasons. By trivial reasons, they cannot have the dichotomy because they have a normal subgroup. We already seen that the existence of normal subgroup immediately ruins the dichotomy property. So if it's a product of two simple groups, you can always play with them, like the trick that I shown here on the blackboard. They will, strictly speaking, they will not have the dichotomy property, but they will have a very natural property that we actually look at. I didn't mention it here. I think that what is even more interesting to look at in the context of compact groups are actually norms which are separable. So norms on the compact group which make the completion separable. There, I think that there are many more interesting doable rigidity results. And if you insist that the completion is separable, which is, it doesn't hurt your question, for example, because this is always we are in the separable world, then semi-simple is okay. They have this property. So they have the dichotomy. So every, okay, this should be stated that every norm for which the closure is separable, then it must be the original norm as a compact group, or it is the discrete. So if you just impose something small, something natural, which is in addition, then you can extend the context of this result to more groups. But anyway, in this context, you always, once you have a target group, and there are many situations when this appears, you have a target group with a norm on it, then it immediately tells you interesting results. Hopefully, the really interesting or interesting, depending on the context, about continuity, or what can you find what can you say about the homomorphism of the group that you started with? But that's yeah. Yeah.
Does the first theorem apply to the ring ZP?
Yeah, ZP,
Yes.
you mean the p-adic or
Yes,
Z
yeah.
one of
the p-adics?
Yeah, yeah. This what I even wrote here, I guess. No, the example.
Okay.
Yes.
Right. So now
Both because it is SL3 of a ring which satisfies it, and because it is a simple p-adic analytic group. So it comes from
for two different reasons.
Yes.
So, and what about SL3C? So SL3C.
SL3C doesn't have even its own. I mean, it doesn't have any. It only has the discrete. SL3C, SL3 of a field. It is boundedly simple as an abstract group. So for any field, look at SLN of the field, it is boundedly simple.
Yes.
So, and this is very elementary. Boundedly simple means that from any element, you can get to any element by a product of 100 conjugates.
Yes.
So this immediately means that all the norms would be discrete.
Okay.
It's very easy to play with it. This is why I mentioned before that such results for SLNQ, that every node is, they are trivial. But when the group is actually finitely generated, finitely presented, and it does have lots of normal subgroups, those groups which have the property that every norm of them is zero, this is a completely new phenomena. Those finite central extensions of
okay.
Yeah.
Thank you.
And there is a last question.
Hi.
About this exotic norm on Z at the beginning, there is a result of Michael Liedelstein in 1964.
Okay, so
that's
you beat the
a
record.
self-isometry of a Hilbert space which has non-bounded orbits but no fixed point. So it so the closure cannot be even locally compact.
Yeah, yeah, okay. Yeah, yeah, you know, we didn't we traced something in the 70s, but yeah, okay, thank you. So I apologize to yeah, but they always require some work. I mean, it's not right. I mean, to construct this.
It's really elementary. It's like a
no, of course it's elementary, but one needs to. There is maybe just one. Okay, I'm sorry, just one word. Inside the proof, I will not because I want to leave you with a really nice question. Inside the proof. For SL3Z, for example, there is this action of, we are not surprised to see the action of SL2Z on Z2, you know, the standard linear action. And one of the hearts of the proof is showing that if you have a norm, just a norm in the sense of this, a norm on Z2, which satisfies, you know, the basic properties here, it's abelian, so the conjugation doesn't, you don't need it. If you have a norm on Z2, which is non-discrete and it is invariant under SL2Z, then it must be compact. Okay, this is a very crucial kind of ingredient. But I'm sure that this should be extended to thin subgroups of SL2Z. So you, in the proof, one does use the fact that it's full of SL2Z or finite index subgroup for SL2Z. But I'm pretty sure, and we cannot do it. There are many interesting, and I will finish with this, many interesting kind of questions that arise in all this discussion. So if you take any thin subgroup, so some subgroup for SL2Z of infinite index, which is not virtually cyclic, and it acts on Z2, and you have a norm on Z2 which is invariant under gamma, is it still true that this norm must be compact? And I will leave you with that. Sorry.
Let's thank the speaker again. So now we will have 2 mini talks, and then I remind you we will have the group photo. Okay, so the first of the 2 mini talks is by Tom Ferragut. And is about geometry and rigidity of quasi-isometries of horospherical products. Thank you very much.
Yeah, thank you. And thank you for everyone who participated in the organization of this really nice conference. And thank you for having me here. Okay, so the story of this talk is diving into the geometry on a family of metric spaces, which are called horospherical products. And just to have a link with other talks, these horospherical products contain notably the sol-like groups we talked about in previous days. Okay, so I just want to give you first a hint on what is a horospherical product. Okay, a metric view of what it is. So first, take a Gromov hyperbolic space, either a tree or just H2. There exists a model where you just take one point of the boundary, send it upward to infinity, and then geodesics look like that. So you first need to increase your height, then decrease your height. Okay, this is how I picture a Gromov hyperbolic space. And to construct the horospherical product, you need two such spaces. You take one that you put in one specific direction. Okay, so in that direction, you need to go up before going down. And in the other direction, you take another space, but you flip it upside down. So in the other direction, it looks like that. Geodesic, first go down before going up. And in this talk, we'll notably ask, okay, so what's happening diagonal? Do you have to go up? Do you have to go down? What's happening? But first, why are these spaces interesting? So, yeah, or sorry, we'll look at the shape and the length of their geodesics, and also we'll see that they are really rigid to deformations. And this can be explained as a geometric rigidity of their quasi-isometries. Okay, so why these spaces are interesting? So it's included in the scheme of Gromov to classify finitely generated group up to quasi-isometry. And there is some current rigid classes, which mean that there is classes of groups such that if you are quasi-isometric to one of them up to finite index or finite extension, you are actually one of them. And for example, free abelian groups are QI rigid, and also nilpotent groups and hyperbolic groups. Okay. However, in the world of finitely generated groups, there is a class of group which is not QI rigid. It's the solvable groups. So Arnar Eschler proved that there exists a non-solvable groups, which is not a finite extension or a finite index subgroup of a solvable groups, but which is quasi-isometric to a solvable group. However, in the Lie group context, it's harder because there is still an open conjecture, the one of Carnot, which say that maybe we can just classify up to quasi-isometry this triangulable groups, okay, up to isomorphism. Okay, so what about horospherical product then? So first, there were quasi-isometric classification of some finitely generated solvable groups obtained by Fabre and Mosher for Bohm-Slag-Solitar solvable groups. And then 13 years later, Eskin, Fisher, and White obtained same classification up to quasi-isometry for the solved geometry, some of the solved geometries, and some distal lithographs. The thing is that these three families of example, Bohm-Slag-Solitar groups, the distal lithographs, and the solvable Lie groups, are all constructed as a horospherical product. And it's thanks to that construction that they managed to prove that they were quasi-isometric classification. So the idea of this talk is to give to try to generalize as much as possible this construction of horospherical product and to see whether or not we can achieve such quasi-isometry classification. Okay, and just a little candy. With this result, they Eskin, Fisher, and White also managed to prove the existence of a transitive graph, which is not quasi-isometric to any Kähler graph. Okay, this is just a really nice result where, so it's transitive. So the isometry group acts transitively. So it really looks like a Kähler graph. It has everything to be a Kähler graph, but it is not quasi-isometric to any Kähler graph. And that was the first time they proved such an example existed. Okay. So before talking about horospherical product and how do we construct them, we want to talk about the pieces. we use to construct the horospherical product. And such species in our context is Gromov hyperbolic spaces. And we will add one more condition, which is the Boozman assumption. So take a geodesic proper delta hyperbolic space. Okay, so geodesic means 2 points, there exists a geodesic between them, proper, so metric groups are compact, and delta hyperbolic is the metric equivalence of negatively curved. Then we add the Boozman assumption, which is that the distance between two geodesic evolve convexly. So this is kind of a strong assumption because it implies uniquely geodesic. So just by that assumption, you remove all Gromov hyperbolic groups, for example, which are not trees. However, we think that this assumption can be removed, but it makes everything more technical. So for now, we just stick about Gromov hyperbolic Boozman space. Okay, so examples are all cat-1 space are such groups. That means that Heintze group are geodesic proper delta hyperbolic and Boozman space, where D is a derivation that contract the nilpotent component. Okay. We also ask N to be simply connected. And because we have all Heintze group, which are negatively curved Riemannian manifolds, we also have all hyperbolic spaces. And for example, H2, that can be viewed as R2 with that specific Riemannian metric, where when you increase the Z direction, the metric along the X direction is contracted. And this is already a point of view where you can see that to travel along the X direction, it's much better to increase your height, so that to travel along the horizontal direction, it's much cheaper. Okay, here I use the log model of the hyperbolic space. So it's just a upper half plan, but you compose the Z coordinate by the logarithm. Okay, so we have all R2. And it's important in our case because we will flip spaces upside down. So we want all the Z coordinates. And discrete examples are more specifically regular trees, okay, infinite trees, where you can have such a model by choosing a geodesic ray, sending it upward to infinity, and then just make your tree lying on that geodesic. Now, I want to define two more notions on these hyperbolic spaces. First, the height function. For those who knows, is just the opposite of the Boozman function. So you take that specific point upward to infinity on the boundary, on the Gromov boundary that you choose, and the height just computes how close you are to the point at infinity upward. So the more you go up, the higher the height gets. For example, in H2, the height function, it's just the Z coordinate. And in any Heintze group, when you precisely choose the specific upward point at infinity, the height function is just the R coordinate, okay? And in trees, the height function is just if you go up by a vertex, the height increased by 1. So it's really like the height in your space. You can, and the level sets of these height functions are called horospheres. And this is where comes the name horospherical products. Second notion I want to just point out is vertical geodesics. It's just a specific set of geodesics that goes upward to infinity, okay? In Heintze groups, it's exactly the geodesics that are only parameterized by the R coordinate, and the nilpotent coordinate doesn't change at all. And because we know that H2 is Gromov hyperbolic, we have, again, another way of seeing that a geodesic looks like a bridge, because this geodesic is included in the neighborhood of the two other vertical geodesics. So you just follow one vertical geodesic until the metric is sufficiently contracted that you can jump to another one and follow down the second vertical geodesic. So any geodesic segment is included in the neighborhood of 2 vertical geodesics. So everything happened with vertical geodesics, basically, in hyperbolic groups. Great. So now we have everything to define the horospherical products. So the definition is take 2 Gromov hyperbolic spaces, specific point on the Gromov boundary, their respective height function, and then the horospherical product is a subset of the direct product. Okay, so you take just the set of couple of points with an additional condition that the height adds up to 0. So if you increase the height of one of the 2 points in the couple, you have to decrease the other one. Okay, so because you add one condition, the dimension compared to just the direct product decreased by 1. So it's like a diagonal in the direct product. And why is it called horospherical product? It's because these spaces, it's just the foliation of direct product of horospheres, because any couples in the direct product xz, which is like the horosphere of x at height z, all the point at height z, times all the point at times minus z, any couples have their height adding up to 0. So it's just a foliation of product of horospheres. So example are, if you take the horospherical product of 2H2, you obtain the solved geometry. And if you take the horospherical product of 2 trees, you obtain some Lamp-Leiters group. Then if you do the horospherical product of a H2 and a regular tree, you obtain the 2-Cadet complex of the Bohm-Sachs-Solita group. Okay, and of course, because of that, this construction really relies on the hyperbolic geometry is directly included in the construction. There is a lot of rigidity coming from the rigidity of hyperbolic spaces. And I just wanted to write another example, which is the horospherical product of 2 Heintze group. So if you do the horospherical product of one Heintze group and the other one, basically what it does, it just fuse the 2 R coordinates, and you obtain that it's R acting on the product of the nilpotent component, and the action act on the Lie algebra level by the first derivation on n1 and minus the other derivation. So it's really behaves well. Okay. So now we just defined a set. So we need a distance on this set to have a metric space. And we just take the length path metric induced by the ambient distance. So since the horospherical product lives in the direct product, there is a distance there that you can choose, the L1 distance, L2 distance, anything you want. And then you look at the length of passes that stay in the horospherical product, and the distance between 2 points is just the length of the shortest path between 2 points. And we call such a distance admissible if it comes from some admissible norm on R2, which, for example, include all LP norm, but I won't get too much into detail. And if you take such a distance, you can already describe the distance on horospherical products. And it is as following. So the distance on a horospherical product is up to an additive constant, uniform additive constant. It's just the sum of the distance on the 2 coordinates minus the difference of height. So take 2 points, take the distance of their respective x or y coordinates when you do the horospherical product of f, x, and y, and you just remove the difference of height. Why does that appear? It's just basically, here you have to first move in the x coordinate and then the y coordinate, or the reverse, moving in the y coordinate or in the x coordinate. We'll see that in a second. And if you travel vertically, you move both in the x and in the y coordinate at the same time. So this is why you might gain some distance there. Just to mention, we also need the 2 spaces x and y to be geodesically complete. which means that geodesic can be infinitely extendable, are infinitely extendable. Otherwise, the horospherical product is not connected. And that can be a problem because, yeah, we want like metric space. Okay. And so as I just said, the geodesic can be described as being not in the neighborhood of two vertical geodesics, but all geodesic segments are in the neighborhood of three vertical geodesic. So take 2 points, P1 and P2, look at the vertical geodesic going through P1, through P2, and they take a geodesic that is just a vertical geodesic that is just another combination constructed out of V1 and V2. So the X coordinate of V1 and the Y coordinate of V2, for example. And you know that the geodesic is stay at a bounded distance from this three geodesic. Because basically what it does is, okay, so I travel downward until the two geodesic in the Y coordinate meets. Then I can move in the Y coordinate. Then I have to go all the way up until in the X coordinate. Now, the metric is sufficiently contracted, and then you travel along the X coordinate. And this is already the first time we see that the two coordinate doesn't mix up. Like there are really like splits. So this is what will happen also for quasi-isometries. Okay, now in every talk we have to do a proof. So this will be the proof. Take 2 points. How can you guess that the geodesic look like that? We know that the Morse lemma in hyperbolic space give you that if you go too far away from a geodesic, your length explodes exponentially. Okay, so take a path between P1 and P2 and project it to the X space, the isometric copy, the isometric copy of X in the horospherical product. Then you know that that path, since we are trying to look at a geodesic, it can't go too far from the geodesic as well. So basically, if you take the pre-image of that projection, the path has to follow the pre-image of the red line. And also, if you look at the projection on Y, the path has to follow the pre-image of the blue line. So basically, the path has to go from P1 to P2 by once traveling along the red part and another one at another time traveling along the blue part. But to go from the red one to the blue one, there is only two connecting points, either this one or this one, basically. So the best way is just, okay, do the red, then the blue, or do the blue, then the red. That's it. And the fact that there is two possible geodesics happens only when P1 and P2 are at the same height. If one of the two is higher, then if you start higher, it's better to just go higher already. It's much better to go all the way down, then all the way up again, and then going down. So yeah, that's the proof of the first theorem. Any questions so far? Okay, great. Now, about the quasi-isometry rigidity. So we first need to add some assumption to adapt Eskin-Fisher-White methods to prove some quasi-geometric rigidity. We need our metric spaces to be endowed with specific measures. Okay, so we take x, y, x prime, y prime, some Gromov hyperbolic Boozman space with admissible disintegrable measure that I will detail later. It's just some measures that behave well according to the height function. And then we ask x and y, and respectively the two components of the target space, that they do not share the same exponential growth parameter. I will explain what it is later, but just to give you an idea, for trees, it's the degree of the tree. And in the Heintze group, the exponential growth parameter is a trace of the matrices here, D1 or D2, okay? So it's something that you can have your hand on. It's like, how do the matrix contract the space while going down or up? And then, under these assumptions, we obtain that any quasi-isometry KC quasi-isometry between two horospherical products splits in the two coordinates. There exists a quasi-isometry of x, a quasi-isometry of y, such that quasi-isometry is just the product of the two maps. So this says you that it doesn't mix x and y at all. Like just everything happens on x and on the side on y. And not only that, but because this map is still a map of the horospherical product, if you take 2 points y and y prime that have the same height, then by phi, they must be sent to the same height also. So the quasi-isometry send horospheres or product of horospheres close to product of horospheres also. So not only it respect the x and y coordinate, but it also send level lines to level lines. So it's really, really rigid in a sense. And using that theorem, you can obtain using, so basically, once you have quasi-isometry on x and y, because you know that they are height respecting, they fix the point upward to infinity. So in Heintze group, using the Pensée derivative when the nilpotent component are Carnot group, you can obtain that the two such solvable Lie groups are quasi-isometric if and only if they are isomorphic. Okay, when the derivation are Carnot derivations also. Okay, and what you can do also is describe the quasi-isometry group of such solvable Lie groups, even when the two nilpotent components are not Carnot groups. And using the recent results of David, Tulia, and Xiangdong, they also managed to obtain that we have that quasi-isometry classification not only when n are Carnot groups, but when they are Carnot by Carnot groups. So they, which attest the Cornelius conjecture for this set of solvable Lie groups. And just a word also, during the computation, we obtain a really nice, not nice, simple quasi-isometry invariant, which is the ratios of the two exponential growth parameter. So for example, if you look at distilled graphs, which are horospherical product of two trees, then you can distinguish them by quasi-isometry just by looking at the ratios of their degree. Okay, and now I don't have time to do all the proof, of course, but I will just try to sketch it a little bit. First, a disintegrable measure is just a method that can be integrated along horospheres. Okay, so the measure of a space is just the integration of the measure of its slices for the height function. We ask that measure to be quasi-homogeneous. So a ball of radius r on a horosphere is roughly the same measure independently on the horosphere you are. And we ask it to have an exponential growth parameter. Otherwise, we can't do anything. It means that if you follow the vertical flow, which is the P function, so the vertical projection, right? If you follow the vertical projection on horospheres, then the measure of what the space you obtain grows exponentially, and with a uniform parameter in the exponential. Okay, if we have that, then we can do the proof, which is the following. I will try to do it in one slide, try to prove the geometric rigidity. So take a quasi-isometry between the two spaces and tile your horospherical product with boxes that I won't detail here, but we can talk about it later, of course. Then, using the coarse differentiation Eskin, Fisher, and White developed, you have that for that suitable scale R, the box of inside the box of scale R, all vertical pieces are almost always sent to vertical. So vertical is sent to vertical, okay? Sent to the coarse differentiation. And then we use a very specific metric construction of horospherical inside horospherical product is vertical quadrilaterals, which says that when you have 4 points linked by vertical geodesics, then they are always in such a configuration that 2 shares the same x coordinate and 2 shares the same y coordinate. Can't be anything else. Then you just take your construction, vertical quadrilateral, take 2 points with the same x coordinate, use the fact that vertical is sent to vertical. The image by the quasi-isometry of this quadrilateral is a quadrilateral almost all the time. Then 2 points with the same x coordinate must have either the same x coordinate or the same y coordinate. So in most of the boxes, you have either x coordinate is preserved or y coordinate is preserved. This is where we use the fact that the 2 exponential growth parameters are different. We know that in all the boxes, all the quasi-isometries split into 2 in the same orientation. Like the upward direction is sent to the upward direction. It can be done also when the 2 exponential growth parameters are the same, but it's much harder. So postpone to later for now, but I promise that I will do it. And then because in all the small boxes, you have that the quasi-isometry splits, then you can just basically glue everything together and obtain that on all boxes at a sufficiently large scale, the quasi-isometry splits. And then you take 2 points at the same height and you show that for a sufficiently large box, the quasi-isometry almost preserve the height. And then you obtain that on the whole space, the quasi-isometry splits on the 2 coordinates. So basically it's really this structure that fixes the coordinates and the fact that concentric differentiation that sends verticals to verticals. Okay. And some last word for perspective. Of course, there is some assumptions that we want to remove. So the exponential growth parameter being different, the Boozman assumption, of course, we want to get rid of it. We have some ideas, but we still have to do it. And there is many ways to generalize, like increasing the rank. Irene Peng managed to do that for metabelian groups. So using similar techniques as she did, maybe we can generalize to RP, semi-direct product of the positive and negative commuting contraction. Of course, horospherical product of many number of Heintze groups. That is somehow related to this. I mean, you increase the rank of the abelian group acting. And finally, the thing that would be really amazing to progress in is the first non-positive and negative commuting part via the action of R. Understanding the geometry or their quasi-isometry even would be really interesting. And yeah, I think that's all. So thank you very much.
Are there questions? I give you this one.
Hi. So one question. You mentioned that the geodesically complete assumption was related to connectivity of the product.
Yes.
Can you explain that a bit further?
Yeah, sure. Basically, it's because there is a really simple counterexample. So if you take Z, okay, and you take an additional point here, basically the height is like 0, 1, 2, 3 if you take the point at infinity here, and this is -1, okay? -1. And if you take another space, but you just shift a little bit the height, so here it's the height 2, 1, 0, here you take the point 1, 3, 4, etc. Then the horospherical product contains that couple of points. But the only one who would be connected to this one is this couple of points. Because like since the distance is related to the sum of the distance in the two components, to have like a neighbor in the graph, you would need a neighbor in like both spaces. However, this couple of points is not in the horospherical product because the height add up to 2 and not 0. So you have like a flying point somewhere and everything else is connected. maybe you can do like rough horospherical product, but
no. Okay, if not, let's thank the speaker again.
Yes,
Tom. So now the second mini talk is given by Yoo Seung-Yeon, and she will talk about embedding balls in groups of polynomial growth into Euclidean spaces. Please.
I thank the organizers for inviting me to give a talk at this conference. So as the title says, I'll be talking about embedding balls in groups of polynomial growth into Rn. So here's the outline, and I'll just begin with some simple definitions. So I'm pretty sure many are experts here, but if a metric space M embeds into a Banach space X with distortion D, then then I'll denote the smallest such bilateral distortion as C sub X of M. And in the special case of LP targets, I will denote the distortion as C sub P. And the basic question you can ask is, given a metric space M, so not you can ask whether it embeds into a target space like Rn or any Banach space X. And once you know that it embeds, you can then ask what are the distortions as here. So I'm just going to spill the beans and just tell the big picture of what I want to talk about. So if we say that denote by gamma a finitely generated group of polynomial growth with a left invariant word distance, then you might ask whether it embeds into Rn or a Banach space. So the big picture is that it depends on whether gamma is virtually abelian or not. If gamma is virtually abelian, then, well, it has like z of n as a cocombinous subgroup, and hence you can easily embed it into some Euclidean space. So that's not a very interesting case. So let's assume that gamma is not virtually abelian for the rest of this slide. And then what it follows from works of Penzu and Sems that it does not embed into any RD. And it follows by works of Shiger, Kleiner, and Leonauer that it does not embed into any LP space for P not 1 or infinity. So to ask more interesting questions, we might ask, if we denote B sub n as the ball radius n in gamma, we might ask what the distortion of the balls radius n in these groups tends to as n goes to infinity. And the answer is that in the case of Euclidean targets, if the target space has large enough dimension, it turns out that the distortion is exactly up to constant multiples of square root log n. And previously, this was shown by Austin, Nauer, and Tao in the case of the Heisenberg lattice. And in the case of the LP distortion for P not 1 or infinity, it turns out that the distortion grows like this function, where the upper bound is a form of a Schwarz embedding theorem proven by Lee, Mendel, and Nauer, and the lower bound is what I'll talk about later in this talk. And again, in the case of the Heisenberg lattice, this was proven by Austin, Nauer, Tessera, and Ferragut and Nauer. So this is essentially the big picture of what is going on. And you might ask, can we make these estimates uniform over n in the sense that what if we look at snowflake embeddings? So again, gamma is as in the previous slide, and you might ask what the distortion of the entire group with the snowflake distance is. And the answer is that for those who know the Schwarz embedding theorem, the Schwarz embedding theorem gets an upper bound of this, and it turns out that you can take the dimension D uniform, and it turns out that these distortion bounds are sharp in these cases. So again, in the case of the Heisenberg lattice, this was shown by Lafort, Sauer, and Tao. And in the case of LP targets, it's similar as before. The upper bound was shown by Lee, Mendel, and Nauer. And in the case of the Heisenberg lattice, the lower bound was shown by Lafort and Nauer. So any questions so far? Yes? Yes. So the notation I'm using here is that I'm saying that A is like similar to B if this is defined as A at most B and B at most A. And whenever I write some subscript gamma here, it means that alpha less than gamma B means that there exists a constant C gamma such that A is at most C gamma of B.
So another question is, this constant is essentially depends on the homogeneous dimension or the some codimension, the index to the some nilpotent groups, or
I conjecture that these constants only depend on the doubling constant of the group, but I don't have refined enough estimates to support that claim. But at least well, I can tell you that this upper bound here depends only on the doubling constant.
Okay, thank you.
But besides that, it's up to speculation right now. And what it turns out is that, as many of you know, such groups of polynomial growth are intimately related to nilpotent Lie groups. So we might ask the same questions for simply connected non-abelian nilpotent Lie groups with a left invariant distance. So we assume it's not abelian, because if it's abelian, then there's not much to talk about. And we're giving a Riemannian distance here because if it has a sub-Finsler distance, then any such ball in such group does not embed into any Rn or LP, because you can just blow up the mapping. So similarly, in the case of Euclidean targets, it was shown by Penzo and Sems that the distortion is infinity. And because of time, I won't repeat the individual references, because what they've shown pretty much is like works for both G and the gamma setting. So to summarize, the ball radius n embeds into RD with distortion square root of log n exactly, and in the case of LP targets, it grows like this function. And same references as before. And if we want to look at snowflakes, then we can look at the sub-Finsler distance, because in this case they do embed into a certain RD. And it turns out that you can take the dimension D uniform here, and it turns out that the distortion grows as 1 over square root of 1 minus alpha. The previous case is the same bibliography as before. And LP targets have this distortion, and same bibliography as before. So this is the summary of my results so far, and yeah. And now I'll spend the rest of the time talking about how to prove these results. So, what I'm claiming in the previous slides are actually two results. So one is the possibility of embedding into some RD, and the impossibility of doing better than that. So I'll first talk about how to embed in optimal manner. So these are the theorems that we just need to prove to deal with these. And if gamma and g are as before, then we can. I'm just claiming that we can embed the snowflakes into RD with the optimal distortion. This actually gives, in the case of balls, you can just restrict the mappings to those balls, and that gives you the distortion, because you can just take alpha equals 1 minus 1 over log n. So, and because any such gamma is quasi-isometric to some g here, we can only we need only prove the theorem for g here. And as usual, we assume G is simply connected and non-abelian. And so here's the proof idea. So if we denote by x1 through xk the left invariant horizontal derivatives of G, then we follow the proof of the Aswad embedding theorem, where we inductively construct our embedding. We make a map that works at scale, a certain scale and above. And we add mappings, component mappings that read off smaller scales. And the way we do this is that given a map psi that oscillates, that reads off scales a and above, we want to construct a map phi that oscillates at a lower scale 1 with such that its derivatives are perpendicular. So if we have this, and we can just continue making the component mappings. And the reason we impose this perpendicular condition is that this allows us to make the distortion 1 over square root 1 minus alpha, not 1 over 1 minus alpha, which would come out from the usual Weierstrass type summation. And naive attempts to solve this would be to just say, let's use Leibniz rule to solve this, but this creates loss of derivatives when passing from larger scales to smaller scales. So we go around this by the following 3-step procedure, where we first develop some little Paley theory that works for bilateral embeddings. We get around the loss of derivatives issues using Nash-Moser iteration, and we will need to extend orthonormal vector fields in a certain nice way. So here's some formalities. X1 to xk are the horizontal derivatives. You can define mth derivatives by iteration, and we define the C0, C dot 0 alpha Helder spaces, and by iteration and using the nabla, we can define the rescaled CM and CM alpha norms as usual. And the little Paley theory that we claim is the definitions of such so the little Paley theory claims that if we have any C0 mapping, we can decompose it into its component mappings with nice properties. So these component mappings were constructed by Fourier, Elzy, and Veneruso, and that they have these good properties in the case of the Heisenberg group was proven by Tao, and in the full case of nilpotent groups, this is what I claim. So this is just the usual property of decomposing a map into its little Paley components. And these just say that these become very, these components are regular. So that's that. And so given the knowledge of the function spaces and little Paley theory, we can express our aforementioned iteration scheme in the following manner. So if we define this by linear form as above, then assuming that psi is a mapping that oscillates at scales a and above, which means that this is true, then we want to solve this bilinear equation with a mapping phi that oscillates at scale 1. And the idea to remedy the loss of derivatives is the following way. So we first begin with a solution to this equation, and which does not involve loss of derivatives, because this automatically has higher number of derivatives by the Paley theory, and then we use Nash-Moser iteration to correct phi tilde into a true solution phi. And here is the Nash-Moser iteration scheme. I probably won't be able to explain this in detail, but it just says that if psi is regular, then we can correct this a solution to this into a solution to this with such that they're close in appropriate norms. I won't talk much about this. And I talked earlier about an extension theorem for orthonormal vector fields, and it is required in solving this particular low frequency equation. So the idea is that to solve this, we just take derivatives of this and then view them as orthonormal vector fields, and then extend to get phi tilde. So here's the main novelty of the part of proving embeddings, which is that if X is a k-doubling metric space and M and D are numbers with a gap depending only on K, and if you have one Lipschitz functions V1 to Vm on X that form an orthonormal system, then you can extend to you can add a new vector with a certain regularity, such that the larger system is also a orthonormal system. And the proof of this is the sketch of proof of this is that we use concentration of measure on the Euclidean sphere and use the Lavoie-Slope lemma. So it's a random construction that works. And in the language of Lie groups, it's just that if you have a Lie group upon a growth, you can extend V1 through Vm to Vm plus 1, such that these rescaled norms are behaving well. And this happens by modifying. So piecing it together, given psi oscillating at scales A and above, we find a non-trivial solution phi tilde using the orthonormal vector field extension theorem, correct it into a true solution using Nash-Moser iteration scheme, and then use induction. And then you get a family of mappings phi n and take a limit along some ultrafilter. And that's the proof of the embedding theorem. I think I lost most of you, so I'm just gonna, so hopefully I'll be able to regain many of you in this part. So something many of us are familiar with is that to prove that the quantitative non-embeddability, let's first go back to the Panzu-Sem's arguments, which says that if you have a Carnot group G and a mapping into RD, then it says that it should collapse commutators. And then you might think that if we measure the variations of a Lipschitz function f along commutator directions, then it should be much smaller than the horizontal directions. So in the case of the Heisenberg group, if you have a Lipschitz function f, then you might imagine that the variations along the vertical z direction should be smaller than its variations along the horizontal xy directions. And here is the theorem about how to quantify this. So if you have a non-abelian Carnot group G, it says that if you measure the variations of f along a commutator direction and rescale it and take a singular integral, then it's bounded by the horizontal derivative of that function f. And those who saw Robert's talk yesterday would be familiar with this expression, which just tells that the left-hand side can't be large at many scales r up to logarithmic scaling. And in the case of the Heisenberg group, this was proven by Austin Tessera and Ferragut and Sauer. And you can easily see from this that if you have this mapping and f is supposedly some embedding of a ball radius n into LP, then just plugging the Lipschitz conditions into this gives you that f has to have by Lipschitz distortion at least squared log n. in the case of nilpotent Lie groups, things aren't that simple because I haven't been able to find out how to take commutative directions. But if we take V along directions in the final lower central series, then it turns out that you can bound the variations along the vertical direction by variations along the horizontal directions. So that's and that's that gives this is enough to give you the Lipschitz bounds in this case. And in the case of finitely generated groups of polynomial growth, you have a discrete version of the previous inequalities where if you again take V to be like, so what I'm hiding here is that we pass from gamma to its nilpotent finite index subgroup. We mod up by its torsion group and look at the and the resulting torsion-free nilpotent Lie group nilpotent group will have a final central series. And if V is virtually in that lower central series, then it turns out that you can measure the variations of a function along vertical directions and bounded by variations along the horizontal directions. And again, this was previously proven in the case of the Heisenberg lattice by Ostenauer, Nauer, and Laffergan-Nauer. So how to prove this? So again, the discrete case follows from the continuous case. You can take functions and modify them and apply the case of the continuous case. And in the case of nilpotent Lie groups, I used vector validability Stein theory, which I won't present today. And in the case of Carnot groups, we can get the stronger statement by using a version of Sauer's theorem. So the idea behind Sauer's theorem is the following. So if you think about Pansu's theorem, it says that if you have a Lipschitz mapping from a Carnot group into Rn, it can be approximated at the microscopic level by Carnot group homomorphisms, but they are precisely the weighted. If you can weigh the polynomials in a certain way, and it turns out that they are the weighted polynomials of degree 1. And the question you can ask is, can we approximate such a Lipschitz function f by polynomials at all scales in some average sense? So here's the way we assign degrees to polynomials. So we just do it with respect to the grading. And to introduce a notation, given the function f on the Carnot group, we denote by a, d, x, or f the best L2 approximation amongst the degree d polynomials over the ball radius r at x. This is what that's saying. And then we use this somewhat horrendous singular integral to measure the variations of how far f is from a degree d polynomial. And what the Sauer has shown is that in the case of Euclidean space, this expression is equivalent to the LP norm of the alpha fractional Laplacian up to constant factors. And it turns out that this still works for Carnot groups. And in the case of the Heisenberg group, it was partially shown by Fassler and Orponen that this statement is true. So so Robert talked yesterday about embedding into L1, and this is much harder because in the previous slides we had good properties because LP was uniformly convex, and now we don't have that. And the big picture is that Chigger and Kleiner showed that the Heisenberg group fails to embed into L1, and Ericsson, Big, Gartland, Ledona, and Naples, and Nicolucigolo showed that there is no biological embedding, if any, non-abelian simply connected nilpotent Lie group into L1. So based on our vertical versus horizontal inequalities, we can ask, given a nilpotent Lie group G, whether there exists exponents Q for which this inequality holds, where V is taken to be a certain nice vector, and yeah, and these inequalities were actually proven for the Heintze group by Nauer and Young, and the upshot of these inequalities is that if this were true, it would tell us that the balls of radius n in those groups would have at least distortion log n to the 1/qth power into out 1. So this is, I guess, a interesting future direction to think about. And here's a summary of what I've talked about today. And yeah, so this is the Bioch's bounds into RD is given by square root log n, and into LP is given by and in the case of snowflakes, they are given as this expression, and we constructed embeddings using these three ingredients, and we showed the non-embeddability using Dern-Searle's theorem, and I guess that's the end of my talk.
And other questions? Yes.
I have a question. So if we look at Carnot groups and then we look at the sequence of Carnot groups on which the nilpotency step gets bigger and bigger, we expect that this should be harder and harder to embed. Is this true? Or maybe the precise question maybe is like in this theorem of yours, there are these constants that depend on G.
Yes.
Okay. Can you say that actually that depends on the step of the group and they're getting worse in the step, or maybe they're actually not really blowing up with the step?
I would say that, well, for the least, these constants depend on the doubling constant. So the doubling constant will be bigger as you take larger steps. But the thing that was surprising was that you already have this best behavior for step 2, and my guess is that the obstruction we have against embedding comes from Panzu's theorem, which tells you that having non-trivial commutators is what blocks the group from embedding into RD. And I guess that already we face the biggest difficulty in step 2, and later on, well, and for higher steps, we don't observe much more worsening because we already went through the biggest difficulty, which was step 2.
But wouldn't you say that if even for a Carnot group embedded in the Euclidean space, then the directions along the second layer are stretched less than the one in the third layer? So say we have a Carnot group of step 3.
But as well as the embedding theorem already tells you that you can embed with the certain square root log n into L2, for example.
Mm-hmm.
So you already have the possibility of embedding, and the lower bound is given by step 2, and I don't think step 3 or higher introduces further factors. I don't have a good explanation for this, but
okay.
The only thing I can observe is that step 2 already gave us the worst behavior, okay. And there's no room for this. There's no room for this to get worse.
Mm-hmm. Okay.
Are there other questions? Yes.
Hi. I just wanted to point out this vertical versus horizontal inequality and the loss of derivative. This actually goes back to an argument of Ormander, who was trying to prove the famous Ormander theorem for subelliptic estimates. And this can be done using the Baker-Campbell-Hausdorff independently of the group structure. So a lot of these estimates can actually be generalized. I wonder if you have ever, or you're aware of embedding theorems or lack of embedding theorems for more general non-group sub-Riemannian structures.
Well, it does seem, well, what we could try to get for free is we could try to take a sub-Riemannian manifold, approximate a neighborhood by a Carnot group, and try to like force these estimates into that by sheer approximation. But I haven't been able to work out that details. But I would imagine that, for example, if you have like some vectors and sub-Riemannian manifolds spanning the tangent space by brackets, you could probably measure these vertical directions along the exponentials of the commutators.
Exactly. Yes. That's exactly the setup of Mander's estimates. Yeah, they really look like the ones that you have in every step, actually. Yeah.
Thank you.
Are there other questions? Okay, if not, we can thank the speaker again.
Okay, well, welcome back to the afternoon session. Our first speaker will be Roman Sauer, who will give his 5th talk here during this week. Thank you very much for that. And he's going to speak about higher property T and the cohomology of arithmetic lattices. Thank you.
Thank you very much. Thanks again to the organizers. A lot of opportunity to do work here. So I will report on joint work with Uri Bader. And I thought that somehow audience would be divided. We have some of the absolute experts on property T here, but we also have probably the other half that for whom this is not somehow their daily bread. So let me start by explaining these words in the title first. So property T is a definition that Castan made when he was 18 or so. And it's a very fundamental property. So we're looking at this property in the context of, say, locally compact groups or discrete groups. And one says that such a group, G, has property T if there is a compact subset in G, not a subgroup, a compact subset, and some small epsilon, such that the following property holds for the unitary G representation. So the property is that any unitary G representation that has a K epsilon invariant vector, unit vector, so something that's almost invariant, but not quite necessarily, actually has an invariant vector, a non-zero invariant vector. So non-zero, or let's say unit vector. And K epsilon invariant is what you probably could think it is. It just means that if you translate by elements in this compact subset and look at the distance to the original vector, then it's smaller than epsilon. So such a vector satisfies this, that this is at most epsilon when you run G over over this compact subset. Then you would say that this vector V is K epsilon invariant. So it's kind of rigidity property if you want. And there are many, many alternative characterizations of this property. An alternative characterization that plays a role in this talk is a theorem by Delorme-Guichadet. And it characterizes property T by a vanishing of the first cohomology. So somehow although I talked about nilpotent groups in the mini course, in some sense, the mini course is not such a bad preparation for this lecture. So if you have such a locally compact G, then it has T if and only if the first, and in the case of continuous G, let's say continuous cohomology, vanishes for any unitary G representation. Another characterization that maybe at this point not totally clear why I bring it up, but it will be important in a few minutes, is a theorem by Yehuda resolving a conjecture by Vershik, I think, that says, okay, you can characterize property T similar way, but you only need to look at irreducible representations. Oh, compactly, okay. G has to be compactly generated for this. Somehow all the groups will look later on. Okay, compactly generated. That's if this is 0 for any irreducible G representation, unitary G representation. Or you could say that the trivial representation is isolated in the unitary dual, which is isomorphism classes of unitary representation with respect to topology called the Feld topology. So there are many characterizations, but these two will play a role in the talk. And if you remember the mini course, we had this situation that we had a statement about irreducible representations. And I said, you can decompose any representation by irreducible ones in something called the direct integral decomposition, but somehow cohomology doesn't behave that well with respect to such. And the only thing, well, it's something, but what you can somehow draw from the knowledge of this vanishing for any irreducible is that the first reduced cohomology vanishes with respect to every such unitary representation V. That's a consequence if you know it for every irreducible. So I could have formulated this also differently and say, Yehuda characterized this in terms of vanishing of the first reduced cohomology. So this property T is a property that's sufficiently complicated so that to show that a group has property T is not necessarily a one. I was just wondering whether it was mine, but so it's usually complicated enough that it's not just a one-liner to show that a group has property T. So we just quote theorems that already are in the original paper by Kashtan, that if you have a group like SLD R in the continuous case, or SLD Z in the discrete case, they have property T provided that D is at least 3. which is not surprising, because if you have a group like the integers, it's very easy. For example, if you take the regular representations of the integers, it's very easy to see by these averages that you have definitely almost invariant, so vectors, unit vectors that are more and more invariant. But the regular representation of the integers certainly does not have an invariant vector. So the integers, infinite cyclic group does not have property T. But then if you have any group that has a projection, an epimorphism onto the integers, you could just pull back this representation of Z that has almost invariant vectors, but no invariant vectors. And it would contradict property T for that group. So any group that surjects onto the integers also does not have property T, and SL2Z is virtually free, so you are in such a situation. Yeah, and it's not just SLN, it's if more generally, if you have this in the context of simple Lie groups of rank at least 2. So the rank of SLD is D minus 1. Then you have property T. Okay, so the goal of this talk is to generalize this notion to higher degrees. And somehow the difficult part is actually to deal with groups like this group. So usually the way to prove property T is not necessarily, but usually the way is to prove it for the continuous group and then deduce it for the lattice. Because this property T has this very nice property that it descends somehow to the lattice, and also if the lattice has property T, then the ambient group has property T. So if you have a lattice now, say a lattice in a locally compact group, then gamma has T if G has T. And you don't need co-compact for this. And somehow, I mean, I definition, no, this is a theorem. It's a theorem that's also in Castan's original paper. And I won't present somehow the proof of this theorem, but somehow if you have, say, property T for gamma, if you have property T for G and you want to deduce property T for gamma, then the way to go is to use this unitary induction that we had in the mini course. So maybe it's worthwhile, since we need it in a second anyway, to look at this. So if you have a unitary gamma representation, we define this unitary induction which was then a unitary G representation. And somehow when you know property T for G and you want to deduce property T for gamma, so you're looking at unitary gamma representations, the way to go is to look at this induced representation and somehow try to find a fixed point, an invariant vector there. But the invariant vectors, if you look at this definition here, G is acting on here from the left, it's nothing else. Somehow gamma equivariant maps from G to V that are also equivariant or fixed under G. These are just the gamma invariant vectors in V. So somehow we apply property T up there, find fixed points, and then deduce gamma fixed points for V. So this is somehow how you go about proving this. What you usually don't do in proving this theorem by Castan is to use the characterization by Delorme and Guichadet, because you could also think, if you remember the mini course again, we looked at the Shapiro isomorphism, which said that the cohomology, and in this case, in particular, the first cohomology of G with coefficients in this unitary induction is isomorphic to the first cohomology, but provided that gamma was a co-compact lattice. So for co-compact lattices, you could somehow argue with cohomology, but somehow it's surprisingly hard to use the cohomology to somehow do this passage from lattices to the ambient group G. And Yehuda again was one of the first who really systematically looked at this problem for non-co-compact lattices in the case of the first cohomology. So let me suggest now something that we can do in higher degrees. And I know there are other somehow ways how you could define property T. So let me suggest the following definition. So let's say in the context of locally compact group, locally compact second countable group, G, but could be discrete, of course, has property. Let me actually define two of these properties. So both are called Tn, but with different brackets. And we call it Tn with this corner brackets if the cohomology of G, again, continuous if it's in the continuous setting, vanishes for all relevant degrees up to degree n included and every unitary G representation. And the second is almost the same with one difference. We don't allow all unitary G representations, but only such that don't have invariant vectors. So the same, but for every unitary G representation V with no invariant vectors. Let me denote the invariant vectors by V to the G. And so there are two reasons to why this might be a better notion. Maybe the most important is we have examples. We have very good examples for this. And this seems to be much more a rarer property. So to bring this together with what I already said, so we have in degree 1, it is actually equivalent. So T1 holds if this holds, and this holds if the ordinary, like Castan property T, is true, let's say, for compactly generated. Actually, no, here I don't want to. No, it's just locally compact groups. So in degree 1, one can show that it doesn't really matter. So if you have this vanishing for all the unitary representations without invariant vectors, then you have it also for the ones with invariant vectors. So both notions are legitimate generalizations, so to speak, of property T. And we mainly look at this one here, the latter one. So what do we know about higher degrees? in cohomology. So we know actually quite a lot about it. And if you ask experts, then they very often say, isn't it in the book of Borel-Wallach? Say again? He pointed you to the book of Borel-Wallach? Ah. Okay, he doesn't remember that anymore, I think. But there is, oh, actually, speaking of Uri, let me erase him to get some more space here. So there is certainly a lot of work. And it's certainly not a complete list to name here: Borel, Wallach, Wogan, Zuckerman. So let me just say ... And it's a whole body of work, and it boils down to a pretty precise understanding of the what's called cohomological irreducible unitary G representations for semi-simple Lie groups, or semi-simple groups, even in the p-adic case. Not the lattices, but the ambient Gs. And cohomological in the sense that an understanding of those representations that have some cohomology in some degree. So there are very well understood, but irreducible is essential here. So for example, a concrete statement that you have, if you have in the simple case, and let's say V is my unitary G representation, irreducible, and let's say non-trivial. So non-trivial means here, non-trivial is the same as saying it doesn't have invariant vectors. Then this cohomology vanishes for all the degrees less than the rank. So this is something that one has, which is, if you look at this definition again, already quite good, right? We have this here. And you also can't do better. You certainly do have cohomology with trivial coefficients in general for these groups below the rank. So that's the best you can hope for. But it's this property with irreducible G representation. And now remember the theorem by Yehuda that said in the case of H1, in the case of classical Cauchy property T, it's enough to look at the irreducible ones. And somehow the very first step in our work is to do a higher degree argument of the same, or similar type. We phrase it a little bit different, but this is not actually not that hard. So let me first explain this. And again, very much inspired by the work that was already there. So there's No, I mean, the trivial representation is also irreducible. Basically, I could have said, take an irreducible representation, which is not the trivial one. That's yeah. Okay, so non-trivial, maybe it's a bit confusing, yeah. Non-trivial irreducible representation. Okay, so for such G, okay. I'm claiming the following now. It has rank of G minus 1. And again, I already said that we basically have proven this, but we have this word irreducible here that we have to get rid of. And the problem is, again, this thing that, of course, you can somehow, if you have a G representation in general, you can decompose it into such a direct integral representation. Such that these guys are irreducible. And then you know by this general argument that you find in the book of Guichardet that the vanishing of those, which we know by this work, implies that the reduced cohomology vanishes. But we want it for the cohomology. We don't want it for the reduced cohomology. And now you have to do this argument that was done by Yehuda in degree 1. And let me briefly say, because it's a kind of a cute argument, there is a little caveat in the proof. So somehow in Yehuda's theorem, the assumption was that the group is locally compactly generated. And these groups are compactly generated, but somehow in higher degree, it's a bit more difficult to do the argument for G directly. If you want, I can tell you afterwards why this is more difficult. It's much easier to work with a lattice here. And we do have co-compact lattices in such a G. And the Shapiro isomorphism negotiates between G and V for co-compact lattices. Somehow this transition between co-compact lattice and G is not a problem as long as we have this co-compactness. So I can actually show this property equivalently for a co-compact lattice in G. So the Shapiro will give me, if I have this for the reduced cohomology for G, I have it for co-compact lattice and any unitary representation of the co-compact lattice. And then I somehow do the argument for the co-compact lattice and show this implies the vanishing also for the ordinary cohomology. And then I do Shapiro to bring it all up. So I will actually show, doing this, I will show the following general effect. So if lambda is a group, discrete group now, of type, let's say, F infinity, which means it has a classifying space E gamma with co-compact n skeleton for every n. Another way to say it would be the quotient, what you call B gamma, has finitely many cells in each dimension, but potentially cells in arbitrarily high dimension. And the lattices, the lattices in these groups, they do satisfy this property. And then the general effect is So if you have this vanishing here in the reduced cohomology for every lambda rep B, with no invariant vectors, then we have this. Yeah, lambda, I mean, I apply it to the case where lambda will be a co-compact lattice of G. Oh. But now there's only lambda, right? Yeah, so that was lambda, yeah. Does it clear? It doesn't fully clear up your question, right? So wait a second. You have now a vanishing for the reduced cohomology. You want to lift this to a vanishing of the cohomology. I'm saying by playing around with the Shapiro isomorphism for co-compact lattice, I can reduce this situation to a statement about discrete groups. So I have a discrete group with a certain assumption, and I have a vanishing for the reduced cohomology. And then I show this implies the vanishing of the ordinary cohomology. And via Shapiro, I can somehow bring this back to G and show that this G has this property Tn. That's the goal. Oh, do you prove this? Okay. So you proved it if lambda is what? Okay. This statement? Really? Okay. 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 I was not aware. I want to. I come to ultra filters. Okay. Anyway, I'm fully aware that you won't be surprised by this proof, but let me do it now anyway. So the thing is, if you look at why do you need this assumption, by the way, right? You need it because if you look at the cohomology, then it's given by a complex of Hilbert spaces, and we did this in the course as well, right? It's the cohomology of this nice model. And this has finitely many orbits of cells. So this is basically a finite number, a finite sum of V's, of copies of V's in each degree. So it's the cohomology of a Hilbert complex. And the very general fact is now that if you have any chain complex of Hilbert spaces, like this one, so let's say, how do we call that? Let's put it like this. So this is like a complex of Hilbert spaces now. And you look at the, now I have to check that I easily make a mistake here. Yeah, right. And if I have cohomology of this complex, okay, we want to show somehow that for this complex, there is no cohomology. But suppose you have cohomology in this Hilbert space complex. Then it's a very general fact, which we won't prove, that if you look at the cohomology of what's called the ultra product, then this has cohomology in the reduced. Okay, so bear with me. We go from G to an arbitrary discrete group with that property via this Shapiro reduction. But now I'm saying everything I need is just in terms of complexes of Hilbert spaces. You can forget about the group because the group cohomology is computed by a Hilbert chain complex. And I'm now proving, I'm not, but I'm saying you can prove this very general fact that if you have cohomology in a certain degree of this Hilbert chain complex, then you can look at another Hilbert chain complex where each, in each degree, it's just the ultra power of the original Hilbert space. I will say a word what this is, but it's a new Hilbert chain complex, and this one has reduced cohomology. And the ultra power is, okay, this construction is the ultra power with respect to some ultra filter. It's basically what you do is, so in a certain degree, it's like the L infinity product of those Hilbert spaces, and you divide out a certain equivalence relation. Basically, you divide out those elements, those sequences. This is a product over n many copies, and you divide out those sequences that have an ultra limit being 0 in norm. It's not so important now for how this is exactly done, but the fact is, if you want to look this up, it's a cute kind of mysterious thing. But taking ultra powers, Hilbert spaces are closed under taking ultra powers. And this is a very general, quite easy functional analytic fact that if this is non-zero, then this is non-zero. Now, why does it help? Well, because if you take somehow the ultra power of that complex, it's just the ordinary complex like here with V replaced by the ultra power of V. That's the same thing. So it basically says that if the cohomology, the ordinary cohomology would not vanish, then we would get some non-vanishing of the reduced cohomology in some other lambda representation, which is an ultra power. But we have the vanishing of the, where is it? Of the reduced cohomology as an assumption. So this cannot be, and therefore this has to be 0. And this has to be 0 for all the V's. So there's one mistake in what I'm saying, because we don't have the vanishing of the reduced cohomology for any unitary representation. I said we have it for those that do not contain invariant vectors. So somehow in this argument, I have to take care of the fact that I'm dealing always with unitary representation that don't have invariant vectors. And you have to make sure that if V does not have invariant vectors, then the ultra power of V also does not have invariant vectors. But that's not true in general, but it's true in our setting. And that's the thing that was missing so far from this general fact. I need Kashtan property T for these groups. So let's say we have to add this here, having T, the classical T, because if you look at this construction of the ultra power, an invariant vector in this ultra power is just basically a sequence of almost invariant vectors. And you don't have almost invariant vectors in V if you don't have invariant vectors. And therefore, somehow, you have to use classical property T as well to conclude that the ultra power does not have invariant vectors, but then you can conclude this argument. Okay, so somehow doing this, playing around with Shapiro for co-compact lattices, we can somehow now lift whatever we have from this body of work from first irreducible representations to reduced cohomology of arbitrary representations, and then using this this trick to ordinary cohomology of arbitrary representations. So let me go to theorem A. Wasn't this theorem A? No, okay. But this was that G, this simple G has property T rank -1. So here's a theorem. Now I want to go to the much harder case of lattices. And not co-compact lattice, I want to look at lattices like SLD, SLD Z, I mean. And remember, as I said, classical property T descends perfectly from G to gamma to the lattice and back. And in general here, it's much more complicated, but in this situation, in this classical situation of these groups, it is the case. Then gamma also has this property T rank of G -1. So you have this vanishing of the cohomology of gamma of such a lattice in all degrees and with respect to all unitary representations that do not contain invariant ones. So before I tell you about this theorem, what's the time? Okay. Suppose we have a Shapiro isomorphism for non-co-compact lattices. What would it give you? Well, then the cohomology of gamma, and let's look at it with a trivial representation. This would be the same as G in the induced unitary induction of this. And you remember from the mini course, we always took the splitting here. And this is a representation now that does not contain invariant vectors. So the statement that we had first, that I just proven for G, would tell you this is 0. And you remember that I was already said that mini course that somehow this Shapiro isomorphism is compatible with the restriction map. So you have a restriction map here, which means that if you had a Shapiro isomorphism and you have not this result, but the result we just had about the vanishing of this in a certain range, and the range is below the rank of G, then the restriction map is an isomorphism. So iso 4 star lower than the rank. And again, this is under the assumption that we had Shapiro and what we just said. But this is already, this fact would be a nice improvement of a classical result by Borel about the stable range of this restriction map. So he computed in a classical paper, which had basically his application in mind was algebraic K-theory. And for algebraic K-theory, you're looking at the special linear group. And he had this isomorphism proven for rank divided by 4. But again, if you had a Shapiro, and the whole point of this talk will be to show that there is kind of a Shapiro, then you get this in this stable range up to the rank. So you see that even, forget about this result, even the result we just had plus a suitable Shapiro isomorphism would be would have some interesting applications because this thing is computable. It's not quite the cohomology of the Chevalier-Eilenberg complex like for nilpotent groups, but it's something a little different, the GK cohomology. You can also compute it as the singular cohomology of the compact dual, but whatever way you take, this is computed. And this is in general hard to compute. So you get computations below the rank if you have such a restriction isomorphism. And now I think I motivated somehow theorem B, which tells that, and I come back to this in a second, but I want to say that you have this not just for simple, but even for semi-simple situations. That the restriction map is an ISO below the rank, and also not just for the trivial representation, but for a G representation. All right. And again, I haven't said much about this, but they're very much related somehow, the methods. But there's one difference. The difference is if here you could have interesting situations like products of SL2s that are far from property T and still have an interesting statement. In this situation, if you don't have property T, then your rank is 1. And then there's a statement about the zero cohomology. So this is basically a statement about groups that have property T. I mean, you can formulate like that, but then it's not interesting. This is also interesting in situations like products of SL2. But the proofs are very much related. Yes. Yes. Yeah, this is very general. Yeah. So let me maybe state the last theorem, and then I will tell you about the proofs. And the last theorem is about a situation where you also have a situation of a lattice, but infinite rank. And so if K is a number field, and then there's something called the Adels. It's a, and G, let me just check. G was simple K algebraic, very general again. Simple K algebraic group. And then you have an isomorphism from the Adel points of G with representation in any unitary representation of this group. You can look at the restriction map. And there is a lattice in this. This is a locally compact group. And somehow the rational points, I will give a concrete example in just a second, are a lattice in this group. And this restriction map is an isomorphism in all degrees. And somehow fits together because this is like a situation of G having infinite rank. So let me not go into the Adels now too much. Let me just say there is a consequence of this theorem, which you can write down, which is very nice. And I'm very grateful to Mark, who suggested to look at this at a conference last year. So the consequence of this theorem C is a theorem by Borel. Which is, if you look at SLN or SLD, of R. And in his theorem, he really looked at the trivial representation. Then this restriction map is an isomorphism in all degrees to SLDQ. So what's missing from the Adels are somehow all the finite Adels, but they don't contribute to the cohomology in this situation. So that's why this is really, can be really quite easily deduced from this theorem. And it says that the continuous cohomology of SLDR is isomorphic to the one of SLDQ. So whenever you have a cocycle in SLDQ, then somehow, at least up to changing to another representative of the cohomology class, it is continuous and can be viewed as a cocycle, is coming from a cocycle of SLDR. Okay, so let me now, in the remaining minutes, tell you something about the proof of these theorems, which are all very much related. But I will concentrate on the first one. There should be an A there. So no, it's enough. It's enough. Yeah, you can get rid of all this little annoying. No. Yeah. No. So what's the proof? So somehow, at least of theorem A, let's concentrate on this. So we have that statement for G, right? Our goal is now to somehow go back to the lattice. And as I said before, and we already used it for co-compact lattice, we're also done. We have Shapiro. So somehow the point is really to prove a Shapiro isomorphism, not just to get these nice consequences, but also to prove this theorem out of the statement for G. And somehow the whole work is contained in the following diagram. So you have here, let's say we start with a gamma representation. And we look at the unitary induction map. And then we're interested in this. I should say there is a map here, but we don't know about the isomorphism property of this map. But it turns out there is something slightly better than the ordinary continuous cohomology, which is called polynomial cohomology. And the same happens here. And it comes with a comparison map. So what is this? And we have maps here. So let me tell you about this polynomial cohomology. And I should give a warning because the term polynomial cohomology is overused in literature. There are various, if you just Google polynomial cohomology, you will find many entries and they're not all the same and they can be quite different. So the one I mean was first studied by Kohn and Moscovici in the context of the Novikov conjecture. Actually, when they proved the Novikov conjecture for hyperbolic groups. And it's just, what is it? It's just the cohomology of the standard bar complex where you look at maps. I mean, I could have also taken G here. So maps, polynomial maps from and what is a polynomial map? A map is polynomial if there is an estimate of the value with respect to the norm in V in terms of a polynomial bound somehow by the word lengths of the gamma i's. Something like this. For some k. So you have a polynomial in the word lengths bounds somehow universally the value of this co-cycle. And it's a nice complex, even in algebra. And it clearly comes with a comparison map to the ordinary cohomology by forgetting the polynomial constraint. And now, and I should also say, if you do this for G, there is no problem of somehow confusing different word lengths by a theorem of Lobotsky, Moses, and Raghunathan, whether we take somehow the word length of a compact generating set in G or we take the word length of the lattice, it's really up to constant the same thing, which is it's quite convenient if you somehow descend from G to gamma, not to care about this issue. But it's already somehow a deep theorem that's somehow behind. And now it turns out that this comparison map is an iso in all degrees. This is an iso for degrees smaller than the rank. This is an iso for all degrees. And this is not a fact about locally compact groups in general. This is something very specific about semi-simple lattices. So you use the polynomial constraint, but it's not enough to, it's not completely general. But in this situation, it's an isomorphism. And therefore, we conclude that this Shapiro isomorphism is an iso in the relevant degrees, which is what we need to prove this theorem A, right? Or to deduce it from G at least. So let me now, do I have a few minutes? That would be great. Yeah, very few minutes. So this theorem relies on a beautiful theorem by Enrico Leutzinger and Robert Young. And this theorem says that these arithmetic lattices have polynomial Dehn functions, higher Dehn functions, below the rank of G. Okay, so this is like you're looking at the isoparametric problem in this combinatorial setting. For example, on the classifying space of gamma would be one way to do it. And then somehow, if you have a sphere of a certain volume, you can always fill it by a disk of a certain volume to some exponent. The exponent is like in the Euclidean situation. That works if gamma is below, this works if you look at dimensions below the rank of G. Above, it's not true. And you somehow, you can Okay, I cannot go into how to do this, but somehow this is behind this fact. It's somehow, maybe some of you know this. I'm sure I know that some of you know this. There's a theorem of Mendeleev that tells you that the comparison map from bounded cohomology to the ordinary cohomology. So bounded cohomology is much more restrictive in not setting a polynomial bound, but a uniform bound. And he says for hyperbolic groups, this is not an isomorphism, it's a surjection. And the hyperbolic groups have linear isoparametric inequalities. So somehow it reminds a little bit of that, but crucial difference is that this is about polynomial cohomology. So you also need less than linear isoparametric problems. You need polynomial isoparametric solutions. And there is something that it's a bit harder to explain philosophically, that you don't get an epimorphism, you really get an isomorphism here. So it's from a homological point of view, the polynomial cohomology behaves somehow better than, in some aspects, better than the bounded cohomology here. So you get immediately an isomorphism. Here, the isomorphism, you also have to show it in the continuous situation, but this is basically the symmetric space of G. I'm just talking about the real situation now. I mean, otherwise you look at the building, but the symmetric space is a ket zero space. So you know the ket zero space has polynomial isoparametric inequalities in all degrees. Stefan showed it in this generality and even greater generality. But here, I guess certainly known before in this context. So and that somehow gives you that you have this in all degrees. And then that you have an isomorphism here again, it's something. It's also a higher degree generalization of something that Yehuda did, where he looked at induction from an arbitrary lattice to the ambient group G in H1. So here you really have to somehow look at the co-cycles and use some knowledge about the specific situation, which I don't want to go into, but you have an isomorphism for the polynomial cohomology in all degrees here as well. And that finishes the theorem, or theorem A. Nice stop. Yeah. Oh, I just forgot one thing, but maybe somebody asked this.
Thanks very much. There are more questions and comments.
So just for a little clarification, so I2 of V, that's L2.
L2 G
locally.
V, not local. Not local. That's the point. It's really, this is a Hilbert space.
It's the induced module in the L2 sense.
Because for the local ones, you have the Shapiro isomorphism, even if gamma is not, You're
right. Okay.
Yes.
So
yes.
I mean, the polynomial that it's an isomorphism makes sense somehow, because it's like if you have a constant function and you compute a primitive, it's going to grow linearly. I mean, so, you know, once you don't insist on the exact growth.
Yes, I mean, you put.
I mean, if you put polynomial of degree k, then you would have a different cohomology. That's for sure.
I mean, if you look at this here, if you let's say you use Van Est, and you represent this by a differential form.
Right.
Now, somehow the corresponding chain in the standard complex would be something like you have a tuple, and somehow you make a kind of geodesic simplex out of it, and you integrate over. But somehow the volume of this geodesic simplex, its volume is polynomially bounded by the sizes of the lengths, right, in a ket zero space. Right. And in ket -1, it would be somehow, okay. Yeah. This is basically the surjectivity of this. And for the injectivity, you have to work a little harder, but it's plausible. It's very plausible.
So from the first definition you gave of property T and with almost invariant vectors can be formulated as follows: that the H1 for every unitary representation, the H1 is Hausdorff, right?
Yeah.
And with some
right.
with some uniformity.
Right.
And now, when one proves a property T using formulae like Matsushima's formula or Garland's formula,
right,
one proves vanishing of H1 and simultaneously that the H2 is Hausdorff.
That's true here as well.
I've never seen any use of this observation.
So the general fact is that if you have this vanishing for all representations up to a certain degree n, then you automatically have reducedness in degree n plus 1. Yeah, that's true. For arbitrary degrees. Yeah.
That's a general principle.
Yes. It follows, it's not hard from this Hilbert chain complex to do this argument as well. Yeah, that's true. Oh, this is true if you have finiteness condition. No. This is true. Let's say for discrete groups, you need somehow the appropriate finiteness condition on the classifying space. You always need this somehow co-compactness in a certain range too.
Yeah. Any more questions, comments? If not, let's thank Roman again. Okay, welcome back to the last talk of the afternoon by Xiangdong Xie. He's going to talk about rigidity and flexibility of maps between Carnot grips. Thanks.
It's my honor to have the opportunity to speak here, and also I'm very grateful for the help I got after my backpack was stolen. Okay, so I will start with a basic result in the field, which is the Quenzel differentiability theorem. So this is a generalization of the Rademacher theorem to the case maps between Carnot groups. So any Lipschitz map or QC map is almost everywhere Quenzel differentiable. And in the case of QC map, the Quenzel differential is almost everywhere a graded automorphism. So using this, Quenzel proved his rigidity theorem, which says that any quasi-isometry of the quaternionic harmonic space or the Canny plane is at a boundary distance from an isometry. So there are two steps in the proof. The first step is to show that the Quenzel differential is a constant multiple of an isometry. And the second step shows that if a map has a QC map has a property that the Bantu differential is a constant multiple of an isometry, then it is the boundary map of an isometry. So let's think Luca look at this type of problem, QC maps where the Bantu differential is constant multiple of isometry. It's called a one quasi-conformal map. And there's some regularity result. I think later you have joint talk with Colin. So says that any one quasi-conformal map is smooth. Using this late Colin and Otaze, they showed that one quasi-conformal map is the boundary map of an isometry. Of I should say, so you have a Carnot group. There's a Carnot dilation that so that defines action of R on the Carnot group. You have the associated the so-called Heintze group, and so any one quasi-conformal map is the boundary map of an isometry of the associated Heintze group. So there are some particular examples. That people have looked at. One of them is the Heintze group times the Heintze group. I think it's due to Colin and Riemann. We showed that the C1 QC map has to be a product map. So again, the proof also has two steps. You look at first look at the Bantu differential, and the Bantu differential. So it's a simple linear algebra. Any gradient automorphism of H cross H to itself has to be a product map. Either both directions preserved or switch the two directions. Now, since the map is assumed to be C1, so it cannot jump from one from where the two directions preserved to the other situation where the two directions are switched. So from here, it is a product map. So later on, we remove this C1 condition. So even if you don't assume f is C1, the Benson differential cannot jump from one behavior to another. There's another interesting example, which is the complex Heintze group. So similar to the real case, you can, this is given by 3 by 3 matrices. Now you allow x, y, z to be complex numbers. So Riemann observed that any C2 QC map from the complex Heintze group itself has to be holomorphic or anti-holomorphic. So again, the first step, you look at the Benson differential. The Benson differential has the property that the Benson differential is either complex linear or complex antilinear. And we also removed this C2 condition. Okay, so these are some examples of particular Carnot groups. For more general Carnot groups, there's notion of rigid Carnot groups and non-rigid Carnot groups. So let me record the definition here. So on Carnot group, you have this horizontal distribution. So a contact map between open sets of Carnot groups. Is a smooth map whose differential send the horizontal space to horizontal space. Now, the definition, which is introduced by Heintze and Warhurst. So Carnot group and is called a rigid if for any open set you consider the contact embeddings from U into N. If that form the finite dimensional space, then it's called a rigid Carnot group. Otherwise, the Carnot group is called a non-rigid. They also gave a characterization of when the Carnot group is rigid or non-rigid. That is in terms of the algebra. So Carnot algebra is non-rigid if you consider complexification of the algebra. If in the complexification has an element with rank at most 1, it's if and only if. So. Non-zero element. So this means there's an element here such that adjoint at X as linear map has rank at most 1. Right? Now, for rigid Carnot groups, there's a result by Collin and Otaze, which says that all the C2 global QC maps are affine. So this means it's a composition of left translation and then grid orthomorphism. I think there are two conditions here, which is that the map is assumed to be C2 and also that the results only for global QC maps. So naturally, when I see, you want to remove this C2 condition, but I think right now it's open. In the non-rigid case, We have the following result. Any QC map has to be locally valid sheets. So just contrast this with the result of Baruch. He has a construction of QC maps of the Heisenberg group that changes the host of dimensions or subsets. So certainly these maps cannot be Lipschitz. So just mention this to contrast the results. So these are for the rigid Carnot groups, non-rigid Carnot groups. There's another class of groups that Enrico and I considered the so-called Carnot groups with first reducible first layer. So with near algebra is said to have reducible first layer. If in V1 we can find the non-trivial proper subspace, which part? Right. Yeah, I lost my files. Okay, other than Euclidean groups and the real Heisenberg groups, right? Yeah, thank you. So the Carnot group is said to have the reducible first layer if there's a non-trivial proper linear subspace such that for any rigid automorphism A, okay. So for these groups, Enrico and I have a result. Any QC map of a Carnot group with reducible first layer is Lipschitz. But this result is only valid for global QC maps. Whether this is true for, okay, whether it is the case that any QC map between open subsets is locally Barthes is open. We have proof in a two-step case, but in higher step case, it's still open. So just remark, Carnot groups with reducible first layer include both rigid Carnot groups and non-rigid Carnot groups. Sorry. The two-step case. Only a two-step case, yeah. Okay, so now you see some results here. There are always two steps here. The first step is to get information about the Benson differential. And often you see that the Benson differentials have special forms. And the second step, we try to eliminate the possibility of oscillating between different behavior of the Benson differential. So the same question you can ask for maps between Euclidean spaces. So so instead of H cross H, now consider Rn cross Rn. I get on just open set. Be a QC map. Now, of course, there's no restriction on the differential, but now we can impose conditions on the differential. Suppose we know that the differential either preserve the two factors or switch the two factors, just like the case of H cross H. And you can ask, where's such QC maps also product maps. So suppose so to be more precise, we write on matrices. So either this form or this form, but it could jump. A priori, it could jump from one point in this has this behavior, and another point could have this behavior. Now, question is F then a product map? Turns out the answer depends on the dimension n. So if n is at least 2, the answer is yes. And the answer is no when n equals 1. In this case, there's just QC actually it's a Barthes map. Well, with the following properties. So the differential has the form on a set of positive measure and have the opposite behavior on the complement. Also, the complement also has positive measure. They are not constant, not constant. They could change from point to point. Yeah, it's F is not a product map. Yeah, you can see cannot be a product map. So that's forgot the condition here. What? I guess it's 2 is consequence 1. It is. 2 is consequence of 1. Yeah, right. All right. Okay. Also, F is area preserving. So as a Bi-Lipschitz map of R2 that is area preserving, it can lift to a Bi-Lipschitz map of the Heintze group. So as a consequence of this example, there's a Bi-Lipschitz map of the Heintze group whose by-two differential has this behavior of alternating jumping behavior. So on a set of positive measure, the Bansu differential has the form, let's say, restrict to the first layer, has the form, and also on a set of positive measure, Bansu differential has the form. So that's very different from the case of edge cross edge. So the same from this result, you can see that there's some distinction between the real Heintze group and the other Carnot groups. But you can also ask some questions about the real Heintze group. So if you look at the proofs, the first step is to look at the Bansu differential, and in many cases, there are restrictions on the Bansu differential. So it's natural to also ask the following question. Right. So there are some questions here you can ask even for the Heintze group. So mentioned two questions. They're not really precise. You can make it precise. So we can start the subset of the graded automorphisms of the Heintze group. So let okay, so D is a subset of the graded automorphisms of H. Now let H be a QC or bi-elliptic map. Such that at almost every point, the Bantu differential lies in D. Does this imply that F has some kind of rigidity? So in the case of H cross H, you can take D, you can replace H with any other kind of group. So in this case, H cross H, you consider those rigid automorphisms which preserve two factors or switch the two factors. And our result shows that it can only have one behavior, it cannot have both. So this is kind of rigidity. So you can also ask the same type of question for the Heintze group. You first fix a set of rigid automorphisms. So it's not precise, not because I didn't say what D is. So a more general question is, you consider QC maps or bi-elliptic maps of the Heintze group. You can ask whether there's some structure about the set of Bantu differentials. Yeah. Yeah, so that's I said it's not precise. You're making it more precise. Yeah, it's just a vague general question. Yeah, you can imagine. I think so. So in general, I think for some D don't have rigidity. For some D it should have rigidity. So yeah. So second question is the structure of the set of Bantu differentials. So you can say what kind of set, what kind of subsets could arise as the Bantu differential of QC map or bi-elliptic map. And then, or maybe it has some kind of structure. Okay, so two questions that I don't know the answer. Excuse me. Oh, this particular example, there are 5 elements inside. Anyway, so like C. C1, C. I don't remember the values. Yeah. Yes. So this. There are two others. You need minus V1, minus V. There the set only has 5 elements. There's actually a result about this is yeah. What? Yeah, there's a okay. So maybe see a little bit about the proof. So with differential forms, we know that you have a smooth map between smooth manifold. You can pull back the differential form. So there's a K form. So there's a smooth map. You can pull back. You got K form on M. And basic property of pullback differential form is that the pullback commutes with the exterior differential. So this property also holds for Sub-riemannian maps. So that equality also holds in the sense of distribution. So this is a result of Leshniak. Using this, we can get the proof in the case of R2 cross R2. So here we can pick omega to be the 2 form, dx1, yg dx2. We assume the differential either preserve the 2 factors, switch the 2 factors, then the pullback has the form. Now, using this, since omega is closed, so you get, we'll do this formally. So you take the exterior differential here, you get du dx j equals 3 and 4, dx j dx2. Similarly here, you get dv dx k equals 1 and 2. Okay, so for this to be 0, you see here the dx1, dx2, dx4. See that all coefficient has to be 0. So in particular, so this means that this function u is constant along x3, x4 direction. So that means and similarly v but we know about the assumption. Oh, okay. So you prove by conjugation, assume there's a QC map such that on a set positive measure, the differential preserved two directions, and on a set positive measure, the differential switches two directions. So that means there's a set positive measure. C. Such that U is non-zero on A1 cross. Similarly, there's a set of positive measure such that V is non-zero on R2 cross A2. Now here's the conjugation U on the intersection. Both U and V are non-zero. That's conjugation. It's conjugation. So H cross H case can be proved similarly, except now when you pull back the differential form, we have to use the Bansu differential. Okay. Let's say QC map. And you have a K form here. You define form here. Let's see. I defined using the Bansu differential. So this is defined to be Okay, you apply the Bansu differential to these vectors, you get tangent vectors here. Okay, so you can define the Bansu pullback of differential form. But there's one difference here. For smooth maps between smooth manifolds, the pullback commutes with the exterior differential. But in the case of Bansu pullback, in general, does not commute with the exterior differential. So Bansu pullback does not commute with even when the map is a smooth contact map. But it's not complete failure. So actually, previously, Filipianov proved a weaker version of this commutativity result. So he showed that in some special cases, you do have commutativity. So in the sense of distribution, so in the case, the Carnot group is two-step, and some co-degree 1 differential forms. So we generalized for the Polianov's result to all Carnot groups. And more differential forms. As I mentioned, in general, you don't have commutativity even for smooth contact maps. So it cannot be true for all differential forms, so only for some particular type of differential forms. So now using this, in the case of H cross H, we make a careful choice of the differential form to pull back, and using that to show that the Bansu differential cannot oscillate, cannot jump. So there's careful choice of the differential form. So we showed that the Bansu differential cannot jump from one behavior to another behavior. Okay, so I think that's what I want to talk about.
Thank you. Thank you very much for this very nice talk. Are there any questions, comments?
Thank you. Thank you, Xiangdong. Could you say more about these examples on the plane?
Yeah.
Yes, please. What's so special about it?
Special. The construction is the so-called convex integration. So the construction is so there's this set of matrices. There's additionally there's a and this matrix is not a product. It's cannot is not the form. So F restricts to this is just a disk. What notation shall we use for the disk? I use the D already for the. So on the boundary of the unit square, it agrees with linear map. In the interior, its differential lies in this set. And once you have this, you can propagate. So you can extend by translating. So you get a global Valley-Pitts map. And okay, you see the differential, you see at almost every point is from the set D, and you can say it's not a product map, right? Probably doesn't answer your question. So there's a theorem in convex integration says when you can construct such a map, the condition is that it's not a precise condition. There's such a map. So this A lies in the convex of D. So this has to be defined.